and welcome to NESA 2026 ISEAP Roadshow. On behalf of NESA, a McCaffrey company, our regional co-host, MatGeo Thailand. It is my great pleasure to honor and welcome each and every of you to NESA ISEAP Regional Roadshow 2026. My name is Patarawan Malaisi from MAA Consultant Company. I have the honor to serving you as the Master of Ceremony today. Thank you for joining us here in Bangkok and special welcome to those attending in the online. Today, we bring together partners, customer, researcher, and industry expert to explore how environmental monitoring technologies are helping create safer community, more resilient infrastructure, and more sustainable industry. Before we begin, a quick note for our in-person participants. We would remind you for registration. Please ensure your mobile phone are set in silent mode during the presentation. Thank you. To official open today event, please join me welcome Pairuji Basetto, CEO and Executive Sales Manager of NESA. With more than 20 years of experience in environmental monitoring technology, Pairuji has led the development and international growth of NESA, supporting projects ranging from meteorology and hydrology to renewable energy and early warning system worldwide. Please welcome Mr. Pairuji.
Thank you. Good morning, everyone, and welcome to the NESA ISEAP Roadshow 2026. First of all, thank you for being here today, both in person and remotely. It is a pleasure to see so many partners, colleagues, and industry professionals gathered together here in Bangkok. This event represents an important milestone for NESA and for our regional partner network. Over the last few years, we have invested significant effort in building strong relationships across Asia Pacific. And today, we have the opportunity to bring many of those relationships together in this room. Our target is simple: to share experience, learn from each other, and explore how we can grow together in the environmental monitoring market. The title of today's event, Building the Future of Environmental Monitoring Together. The word together is probably the most important part of the sentence, because the future that we want to build can only be achieved through the collaboration. Why we are here? When we look at the world around us, it is clear that environmental monitoring is becoming increasingly important. Climate change is generating more frequent and more intense extreme weather events. Governments and private companies are investing heavily in renewable energy. Water resources are under growing pressure. Infrastructure owners are demanding better tools and manage risk to improve resilience. All of these trends are creating a growing demand for reliable environmental data systems and actionable information. At the same time, the challenges are becoming more complex. Customers no longer need just sensor or monitoring station. They need complete solutions that combine hardware, communication, software, analytics tools, local support. No single company can provide all of this alone. Success requires technology providers, of course, local system integrators, domain experts, and service organizations working together towards a common goal. This is exactly why we are here in this regional roadshow. Today is an opportunity to exchange ideas, discuss market opportunities, understand local challenges, and identify new ways to create value for our market. One of the strengths of NESA in that we do not see ourselves as a simple manufacturer. We see ourselves as a part of a regional ecosystem. Today, we are proud to work with a growing network of partners across India, Indonesia, Malaysia, Vietnam, and Thailand, supported by specialized organizations with complementary expertise and strong local market knowledge. Each partner represented here brings unique capabilities, customer relationship, and technical competence. Together, we are creating a network that allows us to be closer to customer, respond faster to the opportunity and to the questions. Together, we are creating this kind of network. What is particularly exciting is that many of these organizations operate in different sectors and applications. Some are activists in environmental monitoring, in infrastructure monitoring, renewable energy, meteorology, water management, and early warning, or industrial applications. This diversity is a tremendous asset because it allows us to learn from each other and identify opportunities that might otherwise be hidden. I would like to thank you, our partners, for all their commitment, trust, and support. The growth that we have achieved in the regional would be not have been possible without your help. Why Asia matters? As we look at the partners network represented in this room, today's one question can arise naturally. Why Asia is so important for NESA? But the answer is very simple. Few regions in the world combine such strong economic growth, infrastructure developments, energy transition, and environment challenges. Across the region, governments and private organizations are investing in renewable energy, water management, environmental protection, and risk mitigation. These trends are creating a growing demand for reliable environmental monitoring solutions. For NESA, Asia is not just a growth market. It is a region where our technologies and expertise can make a tangible contribution and sometimes also a difference. At the same time, the diversity of market and customer needs makes local partners essentials. That is why we are investing in this region and why we are building this network together. Now, let me introduce NESA and the capabilities we bring here to support this journey. Through today's event, you will hear a presentation covering a broad and a wide range of applications and technologies. We will explore real-world projects related to debris flow, early warning system, flood and river monitoring, renewable energy, agriculture, and agrivoltaics, environmental monitoring, and geotechnical application. Rather than focusing only on products, we have chosen to organize the event around a real customer challenge and specific case study. Our goal is to demonstrate how environmental monitoring can generate tangible value when technology, expertise, and local knowledge comes together. I encourage everyone to participate actively, ask questions, share experience, and take advantage of the networking opportunity of today. So thank you once for joining us, and I hope you find today's discussion both informative and inspiring for you. Let's begin with the first speaker. I leave the floor to him. Thank you again.
Thank you very much for setting the stage and highlighting the NESA vision of the future of environmental monitoring. We are now moved to our first technical presentation of today. We have heard how important environmental data is becoming strategic asset across multiple industries. The matter understand the technology, solutions, and application that make this possible. We will now take the closer look at NESA itself. Please welcome Gianluca Mastoni, Strategic Growth Advisor at NESA. He is responsible for international business development and strategic growth initiative, helping organizations transform environmental data into actionable intelligence across sectors such as renewable energy, environmental monitoring, and climate resilience. Gianluca, please take us through NESA vision and capacities. For it's yours.
Thank you. Thank you, everybody, for coming. So let's open up this session with a quick question for you. So what do floods, landslides, extreme weather events, and infrastructure failures have in common? So they rarely happen without warning. That's exactly what they have in common. So nature is constantly sending signals. The challenge is not whether those signals exist. The challenge is whether we are able to observe them, understand them, and most importantly, understand what they mean and act before they become a problem. That's why these three words perfectly describe our approach: observe, understand, and anticipate. Because environmental monitoring is not just about collecting data. It's about transforming information into awareness and awareness into action. So at NESA, we believe that every measurement has a purpose. We do not measure environmental parameters simply because technology allows us to do so. We measure because reliable information helps people make much better decisions. It helps communities prepare for extreme events. It helps infrastructure operators reduce risks. It helps farmers optimize resources. It helps energy producers improve performance. In other words, we do measure to prevent losses, prevent downtime, prevent environmental impacts, and most importantly, help protecting people. This philosophy has guided NESA since its foundation more than 20 years ago, and it continues to drive the technologies and solutions we are developing today. NESA was founded in Italy back in 2003 with a clear objective: developing technologies capable of measuring environmental phenomena accurately and reliably. Over the years, we have evolved from a meteorological instrumentation company into a provider of fully integrated monitoring and early warning solutions. Today, our technologies are used worldwide to monitor weather conditions, hydrological systems, environmental quality, renewable energy assets, and critical infrastructures. What differentiates us is our ability to combine field instrumentations, to combine communication technology, data management platforms, and operational intelligence, all of them into one single ecosystem. In 2024, NESA became part of the McAfee Group, allowing us to combine our monitoring expertise with one of the world's largest and leading engineering groups specialized in infrastructure, geotechnics, and environmental protection. Let's take a quick look at our history here. So our journey, as we said, started in 2003 with weather monitoring solutions. Since then, innovation has always been at the center stage of our growth. Over the years, we introduced several technology milestones, including advanced data loggers, IoT-based monitoring architectures, tsunami monitoring systems, which of them are operating at nearly 4,000 meters underwater, and first-class certified wind sensors. We have also participated in important international projects. We will take a deeper look, later on, including climate monitoring networks in Africa and hurricane monitoring system in Central America. The acquisition by McAfee in 2024 represents another important step, creating new opportunity to scale globally and integrate monitoring technologies with highly engineered solutions. At NESA, we transform environmental data into actionable information. Not only we provide high-quality sensors, our systems collect data from the field, transmit it in real time, analyze it, and generate alerts whenever critical conditions occur. We design complete monitoring ecosystems that combine sensors, wireless communication systems, cloud platforms, and automated alerting systems. These solutions help customer monitoring complex environments, eventually detect risks early, and make faster and more informed decisions. Whether it's a mountain valley, a river basin, a photovoltaic plant, or an industrial site, the objective remains the same: improving resilience, safety, and operational efficiency. Data quality and reliability are also fundamental for environmental monitoring. For this reason, our operations comply with ISO 9001 and ISO 14001 standards, while our instruments are calibrated through internationally accredited laboratories according to ISO 17025 requirements. We also align our information management processes with ISO 27001 to ensure data security. In meteorology, our instruments are developed according to WMO, World Meteorological Organization, and several of our wind sensors are MISNET certified and classified as first class according to international wind energy standards. So, as we all know, climate change is increasing the frequency and severity of environmental risks worldwide. At the same time, many communities still lack access to effective monitoring and early warning systems. Our vision is to make environmental intelligence more accessible through scalable and distributed monitoring architectures. We believe the future lies in wireless, autonomous, and highly connected monitoring networks capable of operating in remote and challenging environments. By integrating sensors, data loggers, connectivity, and cloud platforms, we enable customers to anticipate critical conditions and manage risks more effectively. Customer support remains equally important, of course. Our customers work directly with the teams that design and develop the systems, ensure rapid support, quick responses, continuous improvement, and eventually long-term reliability. Today, NESA operates globally. Our systems are installed in more than 80 countries, serving over 1,100 customers through more than 6,000 installations. As part of the McAfee Group, we can combine local presence with global expertise, supporting customers in very different environmental and operational contexts. Our technologies operate everywhere, from tropical regions to Arctic environments, from deserts to mountainous areas, demonstrating their robustness and eventually adaptability. So technology is the foundation of, I would say, everything we do. And FieldLink represents the evolution of our approach to environmental monitoring. FieldLink is a monitoring architecture designed to simplify the deployment and management of environmental monitoring systems, especially across large territories and remote locations. And we will see quite a few of remote locations today. At its core, the system consists of a central gateway connected to multiple autonomous monitoring nodes distributed throughout the monitoring area. These nodes collect environmental data and transmit it wirelessly, eliminating the need for extensive cabling and reducing installation complexity. Each node is designed for long-term autonomous operation, making the system particularly suitable for challenging environments where access, power supply, or communication infrastructure might be limited. The result is a monitoring network that is easy to deploy, cost-effective to operate, and capable of growing alongside the customer's needs, from a few monitoring points to long, large-scale distributed networks. But as you may know, collecting data is only part of the challenge. So environmental information becomes valuable when it can be easily accessed, shared, and integrated into existing operational processes. For this reason, FieldLink has been designed as an open ecosystem that connects seamlessly with customers' platform and workflows. Data can be visualized through our Sunflower platform, providing dashboards, reports, and historical analysis, but it can also be exported or integrated into SCADA systems, GIS environments, digital twins, and third-party application through standard interfaces and APIs. The architecture also supports the integration of both NESA instruments and external devices, allowing customers to build a single monitoring environment instead of managing multiple independent systems. This flexibility simplifies operations, protects existing investments, and enables future system expansion without redesigning the entire infrastructure or the entire ecosystem. As an engineering company, innovation remains a key driver of NESA's growth and product strategy. Today, we are introducing solutions designed to address the evolving needs of environmental monitoring, combining greater accuracy, easier integration, and lower operational costs. The first example is the new RSG2 Class A pyranometer. Developed for photovoltaic, meteorological, and environmental application, it delivers high accuracy solar radiation measurements while simplifying installation, system integration, and long-term maintenance. Featuring integrated diagnostics, digital communication options, and a maintenance-free design, which is quite unique on the market today, the RSG2 combines premium performance with a highly competitive total cost of ownership. So the second product we would like to introduce today is HailGuard. HailGuard is our new solution for hail detection and risk management. In recent years, hailstorms have become one of the most critical weather-related threats for solar plants, agrivoltaic installations, agricultural operations, and exposed infrastructures. Operators are increasingly looking not only for better protection, but also for reliable information to understand what actually happened during a specific extreme event. This is exactly the challenge HailGuard was designed to address. Unlike traditional systems, HailGuard combines two complementary operating modes into a single solution. The first is early warning. When hail activity exceeds predefined thresholds, operators receive alerts that allow them to activate protection measures before the storm reaches the assets. The second is monitoring. The system records impact events and their energy, creating objective evidence that can be used for damage assessment, maintenance planning, and eventually insurance claim. When integrated with our field link architecture, multiple airguard units can be connected to a single concentrator, enabling cost-effective coverage of large areas while maintaining a simple and scalable deployment models. In short, HailGuards helps customer manage hail risk before, during, and after the event itself, transforming weather data into actionable operational informations. And to better understand how this concept works in practice, let's take a closer look at the two operating modes. So we all know that environmental monitoring is entering a new era. As monitoring networks become larger, smarter, and more interconnected, the need for faster data processing, seamless connectivity, and intelligent edge capabilities continues to grow. To address these emerging challenges, NESA is developing IoT Net, a next-generation data acquisition and communication platform designed to redefine how environmental data is collected, processed, and managed. More details will be unveiled in the coming months, so please stay tuned. But let's take a quick look at NESA's application areas. So the real strength of our approach is versatility. Once a reliable monitoring infrastructure is in place, the same technological framework can be adapted to address very different operational challenges. The environmental conditions measured may change from one project to another, but the objective remains the same, which is transforming field data into actionable information that supports safer, faster, and more informed decisions. This capability has allowed us to develop solutions across a broad range of sectors, including meteorology, natural hazards, hydrology, agriculture, renewable energy, air quality monitoring, and critical infrastructure monitoring. So in the next session, I will briefly introduce this applications area and show how the same monitoring philosophy can generate value across different industries and different environments. So meteorology is where NESA was born, and it remains one of our core areas of expertise. Our meteorological systems continuously measure key atmospheric parameters such as temperature, humidity, rainfall, wind speed, wind direction, atmospheric pressure, and solar radiation. Depending on the application, we deploy professional instruments including thermohygrometers, barometers, tipping bucket rain gauge. We also deploy Class A pyranometers and first-class anemometers compliant with international standards. These systems are used by meteorological agencies, airports, research institutions, and environmental authorities to support forecasting, climatological studies, and operational decision-making. The focus is always on measurement accuracy, compliance with international standards, and long-term reliability, whether we are installing a single station or a national monitoring network. Natural hazards represent one of the fastest growing challenges worldwide, especially as extreme weather events become more and more frequent and more intense, unfortunately, should I say. Our solutions monitor rivers, dams, slopes, landslide, debris flows, and water resources through a combination of environmental and geotechnical monitoring technologies. Typical systems may include radar and ultrasonic water level sensors, piezometric probes, multiparametric water quality sensor, rainfall stations, and dedicated early warning devices such as the Hellomac Geo and Hellomac Hydro systems that we will be talking about more in the next few slides. By combining these instruments with wireless communication and cloud-based analytics, we can detect critical conditions and activate warnings procedures in real time. The integration between NESA technologies and the McAfee solutions allows us to provide complete monitoring and early warning ecosystems for both geological and hydraulic risk management. Even agriculture is becoming more and more data-driven, and reliable environmental information is essential to improve productivity and sustainability. Our agrometeorological solutions support precision agriculture, irrigation management, greenhouse monitoring, and agrivoltaic projects. Typical monitoring parameters for this related application include soil moisture, soil temperature, leaf wetness, solar radiation, of course, and air temperature, humidity, and carbon dioxide concentration. So by continuously monitoring crop and environmental conditions, farmers and operators can optimize irrigation schedule, improve resource efficiency, and better respond to changing climatic conditions. So the combination of environmental intelligence, wireless monitoring, and automated alerts helps transform agricultural management from reactive to proactive. Renewable energy projects rely heavily on accurate environmental measurements. Our monitoring systems support photovoltaic, agrivoltaic, and wind energy application through continuous measurement of solar radiation, wind speed, wind direction, module temperature, and other environmental parameters that directly affect energy production. Typical instrumentation for this application includes secondary standard pyranometers, albedometers, net radiometers, ultrasonic anemometers, and surface temperature sensors. These measurements are fundamental not only for operational performance and eventually asset optimization, but also for energy yield assessment, contractual compliance, and project bankability. Project bankability is one of the key terms we will hear more and more during today's session. So for investors, developers, and EPC contractors, reliable environmental data is a critical component of project success. So environmental sustainability increasingly requires continuous supervision of air quality and industrial emissions as well. Our solutions monitor particulate matters, atmospheric pollutants, and industrial gases through sensors capable of measuring parameters such as PM 2.5, PM 10, ozone, nitrogen dioxide, sulfur dioxide, methane, ammonia, and carbon dioxide. Application range from smart cities and industrial facilities to landfill, urban monitoring networks, and indoor environmental quality assessment. The objective is not to provide reliable data that support environmental compliance, but also operational safety and informed decision-making, while helping organizations better understand and better manage their environmental footprint. Of course, even critical infrastructures require continuous supervision to ensure safety, reliability, and operational continuity. Our monitoring systems support roads, tunnels, airports, construction sites, and transportation networks through the integration of environmental, meteorological, and geotechnical sensors. Typical applications include visibility monitoring, road surface condition monitoring, luminance measurements, carbon monoxide detection in tunnels, and intrusion detection systems for critical infrastructures. So by combining these sensors with real-time monitoring and automated alerting, operators can improve safety, reduce operational risks, and implement more effective predictive maintenance strategies. Ultimately, the goal is to protect both people, critical assets, while ensuring uninterrupted operations. But at the end of the day, technology becomes meaningful when it solves real-world challenges. So the following examples demonstrate how our technology and our solutions are being used around the world to improve safety, resilience, and operational performance. Our first example comes from West Africa. Vascal required a reliable climate monitoring infrastructure spanning 10 different countries. In this case, NESA supplied and deployed a network of WMO, World Meteorological Organization compliant weather stations capable of transmitting real-time environmental parameters. Today, these stations support climate research and adaptation planning across the region, providing critical information for understanding climate change and strengthening resilience. Let's move to Italy, our beloved country. So in the Italian Alps, we developed an early warning system for debris flow hazards. We will talk about this better in a few minutes. The solutions combines meteorological stations, debris flow sensors, and automatic alert systems connected through our FieldLink LoRaWAN-based infrastructure. The project transformed risk management from a reactive approach into a proactive model, improving response times and increasing safety for local communities and for local infrastructure. let's remain in Italy, but let's move to Genoa, which is an area where frequent flood events require a more effective monitoring strategy. In this case, we deployed rainfall monitoring stations and river level sensors capable of providing continuous real-time supervision. When predefined thresholds are exceeded, then alerts are immediately triggered and distributed to decision makers, again improving operational readiness and helping reducing flood-related risks. This project demonstrates how environmental monitoring can support both agriculture and renewable energy at the same time. Working with a technological partner, we deployed monitoring stations across vineyards integrated into an agrivoltaic ecosystem. The collected data supports microclimate analysis, environmental supervision, and optimized management for both agricultural production and solar energy generation. So from vineyards and agrivoltaics, let's move now to a very different setting, which is the beautiful tropical island of Mauritius, which is famous for its crystal clear waters, sandy beaches, and year-round sunshine. Actually, next time we will be hosting this event right there. In Mauritius, our monitoring stations contributed to the creation of a national solar map, where accurate solar radiation measurements were collected across the island and eventually helped supporting renewable energy planning and investment decisions. So this project demonstrates how high-quality environmental data can directly contribute to national energy transition strategy all over the world. Critical infrastructure require continuous supervision to ensure safety, reliability, and operational continuity. So our monitoring systems support roads, tunnels, airports, construction sites, and transportation networks through the integration of environmental, meteorological, and geotechnical sensors. Typical applications include visibility monitoring, road surface conditions. So basically, as we said, we can create a complete ecosystems where we can monitor multiple parameters. In these specific projects, and we will tell you more about it, we were able to set up a complete ecosystem, a fully connected infrastructure capable of acquiring data around air quality, intended to protect a beautiful area located in the south of Italy, which is Matera. It's a UNESCO heritage, very small city, which is carved out directly in the stones. And so the local community and the local municipality asked us to create this monitoring ecosystem because they wanted to understand how eventually weather was contributing to eventually deteriorating the stones. Thank you so much for your attention.
Thank you very much, Gianluca. Your presentation very impressive and demonstrate how environmental monitoring technologies can be applied across wide range of sectors, from renewable energy to agriculture to risk management and infrastructure protection. Now we move to the keynote lecture. We are focusing on one of the most critical challenges facing many countries in the region, landslide risk, mountain environment. It is privilege to welcome Professor Dr. Suthisak Solalam, one of Thailand's most respected geotechnical engineer expert and leading authority on landslide behavior, slope stability, and risk management in tropical environment. His research and professional contribution have helped to shape an understanding management of geohazard across Southeast Asia. Please join me. Welcome Professor Sutisak Solalam.
Thank you very much. An honor to be here. Thanks to NESA and McAfee to invite me to speak today. Let's see. Okay. So today my topic gonna concentrate on the landslide behavior and the safety monitoring for the community in mountainous and highland area. In which in Thailand we have many people who live in the highland area and also in the foresty area, which is in the landslide risk area. First of all, let's classify the pattern of the landslide. Actually, if you open the textbook of the landslide, there are so many kind of classification. But if we classify based on, the potential impact and the size of the landslide, perhaps we can classify in 3 types. The first one is the small area because of the cutting the slope and then slide. We call the slope failure. Second one perhaps is bigger in the scale of the village or the area that move suddenly or either slowly down. We call landslide or land movement. And the third one is the debris flow. Of course, this came down because of the heavy rainfall, and then it's mixture between the debris and also the water. So the reason that we need to classify the type of the landslide is relating directly with what type of the instrumentation is appropriate in each type of the slides. In general, if we talk about the slope stability, for example, if we do the slope cutting for the road construction on the mountainous area, which is quite common in this region. So cut and fill. You can see this is the cutting part, and this is the filling part, and then make the road. So when there's rain comes, they're becoming saturated, and then the strength of the soil becoming lower, and then just slide. And then we can do a lot of protection with that, engineering protection. But anyway, even though you didn't do any cutting, but in nature, the mountains is the fact that the mountain will be decay and decompose from time to time, and then starting to erode by themselves. But it's depending on what type of the geological or the parent rock. Now, for example, you might encounter with the rock that is quite vulnerable to the environment, for example, like slaking behavior that can occur. So it means that those type of parent rock can create a fast decay and then slope movement. And perhaps if you have, especially in this day, you have the climate change in which you cannot, sometimes it's difficult to predict the heavy rainfall, and heavy rainfall behavior now is concentrated in a small area, small watershed area. It's easily to create the debris flow in which can affect too many people. So then we can look at on the mountain, and then we start to see that how the landslide and debris flow occur in the mountainous area naturally. Of course, starting from the top, if there's a heavy rainfall, and then the water try to find a way to come down. If the velocity of the flow is too much, it's starting to have the erosion, as just like this one. And along the way, it depends on how much water or precipitation that we have. It could be this big. This is in Khanom area in Nakhon Si Thammarat. I took like 3 hours to climb up here. And then the local people told me that before the debris flow, the flow channel is just like 2 or 3 meters, just like that. So it means that during the debris flow, the water was up there with all the debris. So these are the things that we need to take to consideration of what type of behavior and what kind of instrumentation that is going to be. And then, of course, from the top of the mountain, the flow path, and then down to the toe of the hill. This is the case in Hiroshima, in Japan, in which if the people who live in near the toe of the mountain or even on the slope of the mountain can affected in this. This is the case that happened in Thailand in 2011. One of the biggest case. This is the the highest mountain in the southern part of Thailand, Khao Phanom Bencha, in which you can see the slide, the landslide, the debris flow come down, and then inundate this area, which consists of about three villages. This is the size of the rock that flow down. So it means that if you want to do the protection and also instrumentation, you need to check the parent rock. You need to check what the behavior, what type of the material is going to flow down. Because this is the granitic rock, so that's why it's produce a big rock like this. The mud stone is going to be another story. It's going to be the mud flow, in which you need the other type of the protection and also instrumentation. This is another case in Nan province, in which this photo just show you that landslide can occur anywhere. I guess that if I just paint the green color here, I use AI to put some tree here, and then let you guess that where the landslide gonna occur. Nobody gonna make a correct answer of this one. Maybe they say, oh, this is no tree, this is less tree, something like that. But what I try to say is sometimes nature of the landslide is random. It's random. So it means that if we need to do the monitoring, we should have the monitoring that can monitor the overall picture of the area, and we also have the instrumentation that focus on the risk, high risk area. That will be perfect. The same case that the landslide, that slide come down and then just on the people who live on the toe of the slope, and then in this case 8 people die. So that's why in some country like Hong Kong, there's a regulation that if you there is no construction area in which from the mountain height is more than 50 meters and the slope of 35 degrees, which is the slope angle of the soil material and rock material, that is can come down. So no construction here, and then if it's 20 degrees, so it means it can flow. You need some detailed study, something like that. Otherwise, this kind of thing can happen. This is in Malaysia, in which this high building is built on the toe of the slope, and then one day it just collapsed immediately. Now, in the case of the landslide warning and landslide mitigation, for the people, for the community who live in the mountainous area, which is comparing to the other side of the slope monitoring, which is perhaps like road construction, railway construction. Those are the the project that have the enough budget to do the instrumentation. But for the people who live on the mountain, there may be difficulty for the government to taking care of the people who live over there. For example, let me go to the next slide. I will come back here. In Thailand, out of 77 provinces, 54 provinces is prone to the landslide. And then more than 10,000 villages of people who live on the high risk area, on the prone area, or more than 3 million. I think much more, maybe 5 million people who are the population at risk. So that's why, let's come back here. To make the successful of the landslide mitigation or whatever natural hazard mitigation, we need 3 pillars here. Of course, we need a knowledge of what kind of disaster we talk about. We need social acceptation or social attention, especially the people who live in the risk area. They need to do the cooperation and understand the risk that they are live in. and the policy maker. So we need to match all three together in order to move the mitigation along. In terms of the mitigation, in general, in concept, we have the structural mitigation, non-structural, and adaptation. Of course, today, perhaps we're going to talk mostly on the non-structural, which is monitoring, evacuation, those kind of things. In some countries like Thailand, for the landslide mitigation in the mountainous area, using structural is not possible because there's a law that you cannot build any alien material like construction things on the mountainous or foresty or national park area. So we still working on this to lift up that kind of the law. Okay, let's see the behavior. There's some font, but it's okay. Behavior of the landslide. When you have rainfall down to the slope here, this is the upslope, intermediate, and the toe. There are two types of the water table that is can created. This is the static water table that generally on the mountain is very low, very low water table. And then you might have a temporal water table that is created during the rainfall, and then there will be some infiltration in and create this perch water table. Okay, both of them, this one, if you have prolonged rainfall, this perch water table or the water in this region can flow down and then just fill in the natural water table here and lift it up and creating the landslide at the toe. It means that for the water table near the toe here, if it's increased because of the infiltration, they can create the deep seed landslide. On the other hand, for the perch water table, if you have intense rainfall and then also high infiltration into the ground here, and then they create shallow landslide. So these are the things that we need to understand. So that's why in Thailand, my research and my student, which is we developed the model called DynaSlide model, which is developed for like 20 years already. So the DynaSlide model is a computer model. It's just a software. It's just a script. And then we have the seepage model and also stability model. But in between, this is the model. In between, we have the soil model, the reduction of the shear strength according to the saturation of the soil. This is the connecting between seepage model and stability model. So it means that with this model, you can input whatever precipitation that you monitor into the model, and then you can do the near real-time landslide hazard mapping. Okay, these are the map that we do. Okay, and then we develop this and plug it in the GIS so we can do the landslide mapping in real time. The important part is not about the algorithm of calculation, but about the material. We spent like 15 years collecting the undisturbed sample throughout the country, and then test in the lab to see the behavior of the shear strength that is changed by the saturation change. And then we make a map for the whole country that in certain area that will be vulnerable to the shear strength reduction. And then with the output here, we develop the landslide susceptibility map for Thailand with 30 by 30 meter grid in the mountainous area. It took us about 10 years to do that. And you can download all the information here in order to get the shapefile of this. So it means that with this model, you can predict, you can foresee where the risk area, statically or dynamic, depending on the input of the water. But that's not all. In order to properly, model the hazard, you need another model, which is the flow model, because those is the area that the slide that the slope gonna fail. But where it's going to flow. We need the B-flow model. So this is the case of the B-flow model, in which we can use just Heck glass, which is not so good, but we also use some other model that is Newtonian debris flow. But these are the model that need to develop in order to properly map the risk area in order to properly put the instrumentation in the right place. That is the most important. Okay. This is another example in Chiang Mai just last year, in Pang Ung, Chiang Mai. And then the landslide just occurred just like that. And then we did some LiDAR, and then we see the information from the LiDAR and at that picture. What I'm trying to tell you in this photo is perhaps before we do the sophisticated model just like that, maybe we can do a very simple analysis. Because of, when the landslide occur, it's not just, the debris flow. There are sub-classification of the debris flow. For example, in some certain type of geomorphology, it can create debris flow. Some certain type may be not possible to create debris flow, just debris flood. In some certain type of topography, just the flood. For example, in the southern part of Thailand, in Surat Thani, we don't have much of the high mountain. We just have a large watershed. So whenever the heavy rainfall occur in Surat Thani, so we just have the debris flood and flood only. We never have the debris flow, something like that. So these are the things that is very easy to classify. Firstly, before you go to the sophisticated model. This is the example, that classification of the landslide, debris flow, and flood and debris flood. Let me show you one of the example here. In the case of the Phuket, that we had the landslide occur in 2024. 13 people lost their life, and then including tourists, including the Russian who try to escape from the war, and then they want to stay there in Phuket, and then unfortunate. You can see, this is the debris flow part. And then from this photo, as a geologist, you can see that not only the part of the flow, but you can see this big rock. And this house built over the big rock. So it means that this remained before the time of the debris flow. This big rock is the evidence of the historic debris flow. So it means that these are the things that we need to concern first. See if this is the area that already had the landslide or debris flow or not. With the DynaSlide model, we developed this map, which is the landslide susceptibility map, showing the different factor of safety. Of course, this is the high susceptible for the landslide, and this is the flow part of the event that happened in 2024. This is the flow part. And there's still a lot of sub-watershed that can create the debris flow in other sub-watershed that totally no monitoring at that time. So with the LiDAR drone, we check the information. This is the sub-watershed that the debris flow occur. And this is the sub-watershed that is nearby, but there was no debris flow at 2024. But however, with the LiDAR, we can see some cracks on near the top, near the crest of the mountain here. And then this is the one that is already flow in this part, this one. This is nearby. And nearby sub-watershed, we can see a lot of old debris. It's already oxidized to be a black color. So it means that these also need to be monitored and put the warning system into this area. And then we did some debris flow model. This is more sophisticated model using the Newtonian flow, and then to see. But these are the things also that is quite complicated, because it depends on the assumption that you use, and then depends on the if in the real situation, if there are big tree that decided to fall down and then block everything, which is not in your model, that will be difficult to see the real threats. But however, we succeed in this case to create the landslide risk map, combining the landslide model, the brief flow model, and then check all the people who live over there that is in high risk, moderate, or low, something like that. Okay, with this map, it's now ready for instrumentation because we know who are the risk people, what is the behavior of the area, something like that. Okay, in that case, in Phuket, we could have used the structural measure like this, like in Japan, Sabo Dam, which is quite popular, which is the can prevent the debris to fall down and then generally reduce the gradient of the flow. If you have in series, in cascade, that will be good. And of course, can be a debris flow net like this or something like that. But as I already mentioned, in Thailand, if it's on the mountainous area, these are the things still that not possible to build because it's in the foresty area. But we are working on that. I'm working with the parliament now to lift up these kind of things. This is another case. Now, when we talk about landslide, the international assumption definition of landslide is not just only sliding, but it includes the land movement. So it means that if it slowly moves, it's still considered in the category of the landslide. Like this one, this is the Doi Chang village in the Chiang Rai. Doi Chang is very famous for the coffee beans. Doi Chang coffee beans, very big area. How big it is? Like that. About 6,000 people live over there. On the mountain, on the highland. But however, this area, the soil or the ground beneath them are the old debris or landslide debris that slide down. We call colluvium material, which is very vulnerable to the water, water pressure change, and it can move slowly. In which evident in the village that you can see the tree that slowly leaning, just like that. The road slowly cracks, and then they fix it every year, and then start crack again. And then in this site, 10 years ago, I put full instrumentation. We have inclinometer, we had the observation well, survey monitoring, whatever thing that is needed, just put it in. And then we found that that is very interesting. This is the cross section of the area. This is 2015. This is 2025. So you can see the wall is increasing slowly. And from the instrumentation, we found that the rate of the movement is interesting because in some year, let me show this one. In some year, you can see here. This is inclinometer data, and then it's moved every rainy season. And, throughout the rainy season, it's slowly moved, not stop. Whenever it's rain, it's moved. I noticed this because when I went, firstly, 10 years ago, I went up to the mountain, and then I discussed with the village people. They said that whenever, the village people told me that whenever it's the rainfall, there is the earthquake. You got my point? It's not the earthquake, your house move because of landslide, so it's vibrate, something like that. So he said, whenever it's a heavy rainfall, there's an earthquake. I don't think so. But anyway, with this kind of information, and then with the collecting of the soil data, of the soil sample, testing in the lab, and then recreate the slope stability model, we can create this graph, which is the graph between the rainfall precipitation, groundwater table, and the red line is the factor of safety. So you can see that in all rainy season, the factor of safety is lower than 1. So it means it slowly moves. But because of the gradient, it's quite flat, it's about like 20 degrees, 15 degree, which is, if it's higher than that, it might have been, slide already. Another technique that we use is the de-insar, which is also used in this area as well. And then finally, we know that the thing that triggers the movement is the water, of course. Whenever the water table is going up into a certain level, the soil starts to move. The slope starts to move. So that's why we did some groundwater modeling. We do the detailed groundwater modeling. And then we propose the mitigation method using the drain shaft, in which this shaft going to construct into the ground, and then we're going to have the horizontal drain for about 30 meters, like a fan, in order to collect the water. And these are the things that may be ready to do in this year and next year. Next year we are going to do IEE first, in initial environmental impact assessment, and then after IEE finished, we start to do the construction. This is going to be the first project in Thailand that doing the structural measure in the forestry area, that we have a special request, a special permission from the Department of Forestry to install this kind of structure into the forestry area, which is now is not forest anymore because it's filled with people, but they still call the forestry area. So that's why we can do that. This is another case that I like to show our research, the latest research that we had. This is the case in Yala in Betong in 2024. You can see this is the building, and this is government building, and this is the slide. You can see this slide. Let's go behind this building. This is behind this building. So the building is like a giant wall to block the slide. So the crowd can go nowhere but up, about 6 meters of lifting up. The problem is they want to remove, of course, they want to remove this because they worry about the safety of the building. Otherwise, it's going to push to the foundation and maybe the building going to collapse. But however, it's very dangerous for the people, for the workers who excavate the material here, and this might slide down and then kill them. So that's why, and it's difficult to install inclinometer in this case because it's quite sensitive. So that's why we use another research that we did on the tunnel. This is the April tag, just the April tag, and then you can use this April tag, and then you can check the distance between these two tags or QR code like this. But however, the thing is, it's not just two QR code with the application to check the distance between these two QR code, but it's the algorithm that my PhD student wrote. To collect the information, to analyze, and then train the AI in order to see the behavior of the whole tunnel to move. So we decided to use this one with this slope. So we apply the April tags or QR code in everywhere. And then it's very simple in this case because we can just use the mobile phone, take the video, high resolution video for 1 minute. Morning, afternoon, and then we put into our algorithm to check the movement and behavior of the movement, something like that. Okay, but anyway, this still under or ongoing research, but already published the paper over there. Okay, focusing, if we already known the risk area, the potential risk area, we can do the detailed monitoring. Okay, focusing. There could be the classification of the measurements in about three types. First of all, I call the indirect measurement or indirect monitoring. What does it mean? It means, for example, piezometer, observation well, rain gauge. These are the parameters that when you already measure this parameter, you need to use this parameter, and then you need to further calculate in order to check the safety of it. It's not direct. It means that you need to have the information very well about the geological condition over there, geotechnical data, the topographic, and then you should have some pre-processed modeling in order to be ready if this piezometer showing the pressure like this, what's going to happen? You should put some threshold into the piezometer. This is the same thing as the dam safety instrumentation, the same thing. Direct measurements is the thing that you're measuring directly, basically the movement. Like you can use the in-place inclinometer, you can use SAA, whatever it is, it's showing the movement. And also, if you use the inclinometer, you'll be able to detect the shear plane, in which if you want to do the mitigation, you can do the mitigation properly. Okay, meter also another thing, but meter is like a detection. Detect the movement, and monitor, that if the tilting is increasing or not. Extensometer, and you can use the load cell in the soil nail or rock bowl. That's another thing that can do. For surface monitoring, of course, we can use the LiDAR drone, LiDAR, and also the INSA, as I already mentioned. I got this from the internet and I forgot where it came from, so I'm sorry for the reference. This is just, but it's very good figure to show the overall instrumentation for one slope. We can have the inclinometer, we can have the observation well monitoring, piezometer, even rain gauge also important. The thing is, like you said, it's not just measurement, but you need to understand. This is very important. Understand. You need to understand. It means that you need to compile all the instrumentation data and then evaluate together, not stand alone, not just inclinometer, not just rain gauge, but everything need to compile together to understand the behavior that is at risk or not, something like that. And for example, in this case, is the project that I involved as a consulting. This is the railway to the Chiang Rai, from Den Chai, Chiang Rai. And then you can see the route of the railway over there, the cutting slope. Some slope fell, some slope slide. First of all, we need to do the risk prioritization in order to put the instrumentation into the certain area. For example, this area is, the excavation is very deep, very high, groundwater is very high, something like that. There used to be some slide before. And then these are the things that we need to put the instrumentation. Prioritization is very important. Okay, this is the example in another case that I put the instrumentation on the mountain or the cave in my university research center in Chiang Mai. Okay, we use the instrumentation like this, and also some of the case of the instrument inclinometer for the slope movement, just like that. Okay, so what I'm trying to say is, it's not only selecting the right location to monitor. Of course, you need to have the map, as I already mentioned. You have to have a model, but you need to install at the right location. For example, like this one, if you want to install the inclinometer, where is you going to put it? In the toe, in the middle, or in the top? You need to understand the geological condition first in order to properly install it. These are the things that we need to understand. And evaluation is very important. Instrumentation giving you data. If you put a lot of instrumentation, it's going to be flooded at you, and then you can do nothing. But it's important to understand how to interpret the data. This is very important. This is, for example, the correlation between water pressure from the piezometer and the movement. Of course, if you have also the rain gauge, you can interpret everything together in order to see that we should do the warning already or not, something like that. This is the example of the case in Doi Chang. I don't know what happened with the red color over there, but anyway, just to show you that this is the information that we incorporate the rain gauge, and also observation well, and then calculate the red color over there. That should be somewhere here also. This is the factor of safety of the slope. That use the information of the observation well and the rain gauge in order to calculate something like that. This is tilt meter, of course. For me, is one of the instrument that is very useful. You can install in wider area, and you don't need to drill. You just put in the surface. But however, it's also the instrument that is very difficult to interpret. It can detect if it's moved. You can detect that, but you're not very sure that when it's gonna slide. So the interpretation, this is the example of the interpretation of the tilt meter. Interpretation is very important. Is very important. Okay. For example, we have our own tilt meter made by Professor Apiniti, which is also my colleague. That's why we call KU tilt meter, and then we put in Doi Tung. And then if you just plot the tilt information with the time, you got nothing. You cannot decide anything. So we need to plot in other way. We plot the inverse of the velocity instead of just rate of the movement, but inverse of the rate of the movement. And we can see something from this one. Okay. Finally, I like to focus on the warning system in Thailand, in which I developed with many departments in Thailand. But in general, this is the schematic that we have. As of now, of course, we have the model here. We have Dynaslide model, as I already mentioned. We have another model we call AP model. I will describe it later. Just a minute. But of course, nowadays we can do the rainfall prediction, not just only measurement. We can predict, but the prediction can be done for like 2 or 3 days ahead, which is if it's farther than that, the accuracy and the will be low, something like that. So what we do is in Thailand and many countries actually in the world, we use the precipitation information from the weather forecast. Precipitation, not weather forecast. Precipitation is mean that the prediction of the how millimeter that is going to occur in this area, in certain area, which is more difficult than how many percent the rainfall going to come down. That is another story. So we need the quantified number of the rainfall precipitation, and then we put in the Dynaslide model, which is already ready to be dynamic in itself. And another easier model we call AP model. We send the information to the decision maker, which nowadays Department of Mineral Resources, Department of Disaster Prevention, and then they make decision to give the warning to the people or not. In Thailand, we create the community-based warning system. So it means that we try to we go to the community or the village that they are prone to the landslide, and then let them work with us. We given 3 things. First of all, knowledge. You are in the risk area. What are the behavior of the landslide or the debris flow in this area is going to be? The risk map, give to them. Tools, we give tools. Tools mean that instrumentation. If we put instrumentation, the display going to be in their village, not only by the government, or maybe basic tools, not sophisticated tools, but basic tools for them to operate. And the third one is the regular drills. Of course, this is very important. This is another model that I developed with my student. We call AP model. We have been using this about 7 years already, which is more simple than Dynaslide model. Dynaslide model is more to be geotechnical model. This is more to be like statistical model. Based on our research, we found that if we plot in Thailand, if we plot between 3-day accumulation and daily accumulation, which is the rainfall intensity, and then we have the historic information, historic event that the landslide or the flow occur, we can draw some threshold just like this. So we keep research for 10 years, 15 years, and then we got the threshold that is different in each part of the country. So this is the threshold that you can easily measuring by, rain gauge, and then compare to this threshold, what is the accumulation in 3 days, and then what is the intensity now, to basically, check the possibility of the landslide. And this can be done easily by the village people. You can have the rain gauge, just that, and then, they can collect the information, okay? And then we can, if we have a better, rain gauge, not a daily rainfall, but you have 15-minute rainfall, it's even easier to follow the risk. This is every 15 minutes. So it means that you can keep monitoring on that. Okay, this is the actual, and then we change this threshold into the probabilistic analysis in order to check the possibility of the slide. And nowadays, we use this as the standard for the Department of Mineral Resources together with the Kasetsart University and HII, which is the organization relating with the weather forecast. And then we combine three together, and then we make warning every day, even today, is by our model. Okay, now, if the information found that, for example, in this case, this is today, this is today, this is tomorrow, this is the next day. Okay, they're gonna be the red zone over there. Okay, we send information to the village people, and then village people, they need to have some tools, and the tools that we selected should be simple enough that they can, maintenance and then operate by themselves. We select two sensors. First of all, is the rain gauge. Another one is the debris flow sensors. Okay, this rain gauge and debris flow sensor need to install on the mountain, which is very challenging. And then this is the system that we developed. That the rain gauge will send information of the precipitation in our master station. This can be like 1 kilometer, 2 kilometer. We use the radio signal, signal in order to transmit the information to this one. Okay, and then if there's accumulated rainfall and rainfall intensity exceed the threshold, they're gonna send a signal to the warning box. This is the warning box. We call the household box. It's installed in each house. Because during the heavy rainfall, you can hear nothing. It's very loud. Yeah? So even though you have a very high, speaker, something like that, but it's difficult. Yeah? So we decided to put it in the house, just like that. But of course, before we install, we need to check the topography. We check the geological condition, where to put the debris flow sensor, where to put the master station, where to put the household warning. Okay, so this is in general. Okay, so rain gauge, the before sensor, and then send the information to the radio, just like this, to the master station, checked by the threshold that we have the research on that, and then warn to the people. That is the prototype that we have, but nowadays we have only this in our palm, very small. This is the household warning box, warning sensor. We install in Phuket already, which is the rain gauge over there, and then not yet the biflow, and then send information to master station, and then we have the warning box like this, circulate into the village over there. Okay, and of course we need to work with people so then they can take care the instrumentation, and this is the big thing. For the community base, now we need to have the collaboration with the village people so they can take care. And it's gone. Well, these are the things that I need to tell you when we work in the Southeast Asia, and I cannot say Southeast Asia, not Singapore. In Thailand, perhaps this is the reality. Before, after, before, after, something like that. These are the things that need to take into consideration of the factor of the location of the installation. So it's not 100% academic or theory. Okay, so these are the things that need to be done also. I developed more simple model. we have the sensor that is accurate, that is good, and then information need reliable, sent to the central government, sent to the head of village. But we need to have some more collaboration with the people. So I just use the very simple linkage like this, but I dispatch this linkage to the people. This is one village, one village. We give many linkage to the people in the village. For example, this village has about 200 people. About 200 people, and then we dispatch about 9 of the linkage. Okay, this is psychological things. Let me tell you. So in the morning, 7 in the morning, I ask each one that taking care the linkage to go to the application, line application, to input their rain information into the system. And the system will show like this. If someone already put the information, it will be green. If someone didn't put, it will be white. Now, think about that. If that day some landslide occur, and then there is no input from those guys, who gonna blame? They're gonna blame themselves, right? So these are the things that we created in order to them to taking responsibility by themselves, not our own. We help, of course. We have the model, we have the prediction, we have the pre-warning, we have the sensor, everything, but they need to also help themselves. This is very important. So that's why this is the real situation. At that day, you can see a lot of water. And then they put the information in. Everyone put the information, so nobody to blame. So at that day, they did evacuate by themselves. Not the authority asked them to evacuate, because authority need to have the information, check with the boss, and then report, blah, 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 and then evacuate. But now they evacuate by themselves, which is good, okay? This is another real situation, okay? You can see this. This is bigger area, many villages, about 20 villages in this area. This is Doi Tung area, okay? And then you can see some of the area, some of the village getting red, yellow, green, whatever, and some did not put any input over there, okay? And then if we also combine the information of this is the house, the dot here is the house. We analyze that for each house, what risk level of the house over there. So the owner would know that if there is a red in their village and they live in the risk area, they need to evacuate first. They don't need to wait for the others. Okay, and then now we expand this system, which is very simple. And I use very less money just to buy them the linkage, in which I also made it by myself, even sticker with my team, and then just dispatch. And then this, application, I just ask someone to do it for free. So do nothing with the money. But anyway, what I'm trying to tell you is we need, of course, the reliable, instrument, reliable system, just like NESA, will present to us today. And then, and that reliable, we also need to use not only for the specific area, but for the wide area, in order to look at the big picture, in order for the authority to prepare for the help. That is very important. You cannot, someone might say, oh, my system is very good. No, it's good for the people over there. But in overall, you need to connect with the authorities in order to preparation. And the most important thing is in overall, when you have instrumentation, when you have their system, you need to do the drills. That is the most important, how to use it, when to evacuate. You need to discuss by, the community people over there. Okay. So that's all for my presentation. Thank you very much.
Thank you, Professor Sutisak. Your keynote highlighted the complexity of landslide process and the important combining scientific understanding and practical risk mitigation strategy. I would like to ask if there are any question from the floor.อาจารย์ขาอยู่กับหนูก่อน I think we have some question from the online. The first question, considering Thailand climate and soil condition, what do you see as the biggest challenge in integrating real-time monitoring technology into geotechnical asset management?
Well, thank you. Thanks for the question. I think the challenging things for the monitoring, first of all, I already addressed it would be about, if you have the real time or near real time, we can say near real time monitoring, is how to distribute the information timely to the necessary, to the needed people. Monitoring, of course, we have to look at the big picture here. Detection, observe, evaluation, right? And after evaluation, decision. After decision is the distribution of the information. So the challenging thing is not only for the real-time monitoring, that how you can prepare about the communication and distribute the information to the people who need it, especially who are in the risk area. That is very important. Think about what normally in the mountainous area, of course, you have the cell phone system. But during the heavy rainfall, it's gone. Because the landslide might collapse their tower, the cellular tower gone. And then I discussed with the cellular company. They said that they have the team. If the cellular tower gone, they can, make it back in like half a day or something like that. But they need to initiate the system for another half a day, something like that. So it means that every information that you collected might not have been evaluated correctly because it's no information. So that's why we need to have both systems. The system that rely on, the sophisticated evaluation, and the system that the people who live in the area can rely by themselves if they disrupt by this kind of communication. Any question, please?
Question from the floor.
Yes, please.
Yeah, it's working. Yeah. So, Professor Satisak, first of all, thank you for your presentation. Community-based warning. That's very interesting approach. But you mentioned during your presentation that of course it takes some kind of equipment to be installed and distributed throughout the area that's going to be monitored. From a financial standpoint, what's the approach? I mean, who is financing this thing? It's like local communities, it's like local municipality, what is it?
Well, nowadays, the Department of Disaster Prevention, DPM, and management, the approaching is the community based, like this. Department of Mineral Resources, even though they also do the sophisticated monitoring system, but they also at the same time parallel do the community based. Because in the past, especially like 15 years ago, 20 years ago, that we don't have much of the budget of the disaster prevention. So that's why at that time most of the mitigation rely on the community base. So it means that the government officer go to the village, give them the knowledge, give them the rain gauge, tell them that when to evacuate by themselves, something like that. Yeah, so that's the starting point. But nowadays we have technologies, we have sensors. I must say that in some period of time, when the technology come, when the sensors come, we kind of lack of the community cooperation. Yeah, so we have more weight into the technology, and we left, the community collaboration. Yeah, and that also not quite good. And then we have evidence of the recent landslide that the information from the technology cannot go to the village. So that's why nowadays it's a policy that we come back to combine two together, to work together. So that's why I have this framework that I mentioned, that it should have the community base that can be self-reliant at the time of emergency, right? And also the information, the part of the central government to have the sophisticated model, sophisticated sensors in order to monitor. Okay, welcome.
Thank you very much, Professor. I have one question that you have explained very well, that if you have the models already, and then based on the data you are putting into those models to have the decision-based system, correct? What if the models for a certain area is not available, and then with the local community, and if we receive that, okay, we are facing such kind of flash floods or this debris flow or this, but if the model is not available, what you recommend from where to start? I mean, and how quickly we can support them by implementing such kind of technological sensors, or how? I mean, if the model is not available, what would you recommend over there?
Well, thank you very much for this question. The model that you refer to maybe is a geotechnical model, the B-flow model, which is quite sophisticated and takes time, right? First of all, if the model is not available, we perhaps need to focus on the direct measurement method, like a movement, using inclinometer, using the 2 meter, but those instruments need to install in the right location where the risk is here. So you need to select the risk base, the risk target, and then install directly. Even though you don't have the information of the geological condition, geotechnical thing, you don't have model, but at least the movement can tell you. You can go to use the direct measurements, but you cannot install the piezometer because you got nothing, right? That's one thing. The second thing is the same thing as AP model, as I already mentioned here. Statistical model is very simple. By keep collecting information of the rainfall, and plotting this one. And other country may not. This is from the research. In Thailand, we found a 3-day accumulation, but in other country, 5 days. In some other country, like other country that have the volcanic rock, is about 15 days accumulation. So it's different according to the geological condition. And this is also very simple because you can have the information, you can cross-check with the event that occur or not occur, something like that. So that's another thing.
Thank you, Professor. I think that gentleman in front already asked what I actually intended to ask. I just wanted to ask one more question, is that for someone who didn't have the model, and based on what your experience, what is the reasonable time duration to collect the data that can achieve the result of your large model?
Okay, that's a very good question. In the past, it's very difficult for us. Like 20 years, 30 years ago, when we developed this model, because we need to wait for the landslide to occur. and then when it occurs, we just say that this village had the landslide, and this village, and then we need to look for the information of the rain gauge, of the rainfall precipitation at that time, at that period, which is also difficult. Yeah, but nowadays, it's more easy because of what? We use the NESA technology to map each slide, each scar. That's one model that we have. So we have scar by the NESA, right? And another model, we collaborate with the Department of Water Library in Thailand. We have water, something like that. I'm not sure about the real name, but this the organization collect all the water information throughout the country from every department, and they create the contour map of the precipitation that already occurred in the past. So it means that if we match the scar and then we have the contour of the precipitation, we can have the number of cases more than what we have here. This is my old model. Actually, my new model is working on my master student over there. Is working on it. So we're gonna publish the paper soon. We use NESA and also the contour of the precipitation. Yeah.
Excuse me.
Hello?
Yeah. Thank you, Professor, for this wonderful presentation.
Thank you.
Yeah, you first, yeah, and then later here.
Yeah. So I am from Sri Lanka National Building Research Institute. So we are basically the main focal point for the landslide management in Sri Lanka. So more or less all the presentation is coinciding with what we have experienced and all the community-based early warning and the things you have shown in with the people's like behavior. So we also installed some of the instruments that are working with the solar power. So when we do the once a month monitoring, the solar panel is stolen, all the chain link fence we put it there was taken out. So that is also one of the big problem. We are also dealing with installing the instrument in these rural areas in Sri Lanka. So the question is not related to that, but also we had a research projects coming up. We did to give that debris flow predictions. So unfortunately, what happened is, so it also we use the 1D simulation, the infiltration simulation. So the predicted pore water pressure was not enough to generate the debris flows. So however, there were massive number of debris flows happened. So I'm asking the question whether 1D you use the green lamp model, but I also use something similar. So is it possible that we use the green lamp or the 1D seepage in our prediction model?
Yeah, it's possible. The green and amp or other model like Richard model also work very well. But however, the important thing is the real soil sample. Yeah, so the reason that I will not go back. The reason that I can use the NASLide model based on the Green and Am or Richard model and stability model is because we spent like 15 years collecting the soil sample throughout the country. And each soil sample collected disturbed and then test in the lab for the unsaturated permeability and also the information of the shear strength reduction because of the water pressure increase, something like that. So those are the key elements that to make your model more reliable, right? And it's painful. What I'm trying to say is, even though the geotechnical model, the brief flow model is, if you have enough, or more accurate input information, and it will be quite accurate in some point, but it's painful. You need to have a lot of patience collecting information. You have to have the geologists working closely with geotechnical engineer in order to, collect the soil sample. You may also need to have some flume tests in order to check the flow velocity or the, information of the, of the material that flow, something like that. So it means that if we're not quite ready for that, maybe we need to start with the statistical model, but parallelly, okay. The geotechnical model or is the platform or the basic of the instrumentation. It's good, it's accurate, but the problem is it can warn in the specific area, right? In the certain area. But this kind of model can do the warning in the larger area, depending on the the rain gauge. In one rain gauge, maybe 4 by 4 kilometer. But the accuracy, of course, is not as good as the instrumentation that you install. So you may need to have several system in one area in order to cross-check each other. Yeah, something like that. I heard about Sri Lanka event also last year, right? Last year, some government invite me to have a talk also. Yeah, but yeah, I don't know. It's a very big event. Yeah. Thank you very much. Here.
Namaste, Professor. It was a good presentation because we see first time like this local contribution also towards the warning knowledge and awareness. So my question is, you have shown one portable warning device in the slideshow. So that portable warning device, can you tell us like how does it operate and what are the more details about it?
You mean this one?
This one, yes.
Ah, okay. This basically is a warning box. That's all. It's the same thing as this one. This one is prototype, so that's why it's big. So from the sensor on the mountain, sent to the master box, and there's an algorithm to make decision. And if they're gonna be the warning, they're gonna send to the we call the household box, because it's small, and you can even carry anywhere you want in the range of the system, which is about 500 meters. If it's more than that, we can have repeater, which is okay. But nowadays, I'm working with the Department of Disaster Prevention. We're gonna do another system. So this is the household box in the area, and then we're gonna put into the cell broadcast also. So then that the people who are living in the certain area can get the message warning by the cell phone. We are working on that. Okay.
Question is, what were the major challenges you faced when you were doing hyperlocal, this early warning awareness?
The understanding of the local people. If you go to the village that did not have any experience of the landslide, it's very difficult to convince them. So they say that they've been living there for 100 years, nothing happened. We have 54 provinces out of 77. So let me say this, I don't care. There's a people that in need. Yeah.
Do you see it's working now? Now they are aware?
Well, I'm sorry?
Now they are aware? It's working now?
They are aware. Yeah, especially the community-based system. Yeah, they operate by themselves. Yeah, and then we try to expand that. Yeah.
I think that's a big achievement then.
Okay. Thank you very much.
Thank you, Professor. It was a nice presentation, and I'm also represent the Sri Lanka, and I'm former students of Kasetsart University 20 years back also.
Oh.
So my question is very simple. Can we use your models in our countries, especially the tropical countries at least, or do we have to improve the models using our engineering parameters? Thank you.
First of all, I did not mention in here. You need to have landslide inventory map. That is very, very important at the starting point. The reason that I can do something like this because we start landslide inventory 25 years ago, and we keep collecting. So if you do have landslide inventory, the location of the slide, the type of the slide, what was the precipitation, what was the damage, those are the things. If you have it, if you already have it, you can do this. In some certain area when you have the rain gauge to collect the information. So it means that you need to have the rain gauge that have the information back for about like 15 years, 10 years, something like that. But if you just install the rain gauge last year, it's still okay. Just start collecting information, no problem. But just start to have the inventory map. Okay.
This is going to be the last question from the floor. Thank you very much, Dr. Sutisak.
Okay, thank you very much.
Now we still feel uncomfortable about the natural hazard. We will now move from landslide behavior to the real world application to monitoring and alerting technology from debris flow risk management. Please welcome Domenico Pladino, environmental engineer and senior account manager for rockfall section at McCaffrey. He will present the real-world example of debris flow monitoring and alerting solutions. For it's yours.
Thank you. Just one moment for my presentation. Good morning to all. I'm Domenico Paldino, and thanks, Mr. Professor, because now my presentation will follow up what the professor showed, because it's the same approach to the same problem. We followed a different path, but the results are more or less the same. So I'm very happy to follow your presentation. So, as we know, natural hazards cannot be prevented, but their consequences can be mitigated. This project demonstrates how real-time monitoring and early warning systems can support timely and informed decisions. We know that mountain regions across the globe are increasingly vulnerable to debris flow events. Rapid movements of rock, soil, and water can devastate communities with little warning. Climate change is accelerating this risk with more frequent intense rainfall and melting permafrost. Traditional mitigation efforts alone are no longer sufficient. There's a growing need for proactive monitoring and early warning systems that enable faster, smarter emergency responses, saving lives and reducing damage. So, for my exposition, let's start with the local context. This is the area of Sonico, located in the Central Alps of the northern Italy. It's a landscape of breathtaking beauty, but also significant geohazard. Two main geological features shape the risk profile of the region. First, the presence of an ancient paleo landslide known as the PAL, along the Gallinera Valley. This is a deep-seated, dormant mass movement that has the potential to reactivate under certain conditions. Second, the side valley of Varrabia, which periodically releases high-energy debris flow, fast-moving mixtures of water, mud, and large rocks. These events are typically triggered by a combination of intense precipitation and permafrost degradation at higher elevation. In this area, freeze-thaw cycles, rapid fluvial erosion, and climate-induced shifts in weather patterns amplify the instability. So, we are dealing with a complex system where multiple hazard forces interact and when even modest changes in rainfall or temperature can lead to devastating outcomes. On July 27th in 2012, this fragile balance was broken. We see here a video. After a series of heavy rainfall events early in the month, an highly localized storm cell released an exceptional for the Italian territory 180 millimeters of rain in just under 20 minutes. Taking count that that's nearly a month's worth of rain in the time that it takes to make dinner. The soil was already saturated, and this final storm acted as a trigger, mobilizing around 400,000 cubic meters of debris, which cascades down the valley at a speed reaching up to 10 meters per second. The Reno Bridge, located at the bottom of the valley that connected the villages of Reno and Sonico, got washed away, but the debris flow rate was estimated at more than 1,800 cubic meters a second. Furthermore, from the analysis of the LiDAR images, the average ground level has risen of more than 4 meters. This disruptive force was immense. The main road through the valley was cut off, bridges were swept away, and homes were threatened. The Reno Bridge, one of the key connectors between settlements, was destroyed. But perhaps most alarming was the unpredictability. There were no early warnings. The event unfolded rapidly, leaving very little time for emergency response. This disaster became a turning point. It prompted local authorities to rethink the risk management, not just in terms of detection, alert, and timely evacuation. In the aftermath of the 2012 disaster, authorities moved quickly to understand the causes of the disaster. An in-depth analysis of the river channel highlighted some critical aspects, including the stability of the river banks, made of compacted earth, the shallow depth of the riverbed, and its modest cross-sectional area. Traditional mitigation strategies were then implemented. Upstream banks were built to slow debris, downstream banks were reinforced, detour channels were built, and even the bed of the Oyo River was lowered and widened to accommodate future sediment loads. These were essential first steps, critical for protecting key infrastructures and reducing downstream impact. But they all shared one limitation: they were passive. They didn't detect or predict an event. When dealing with fast-moving debris flow, every second matters. Without real-time situational awareness or warning, these defenses offer no opportunity to evacuate people in order to prevent exposure to lost lives. That's where a more integrated, proactive approach was needed, one that could provide automatic detection and timely alerts, especially during the night or in bad weather, when response time is even more critical. In response to this need, an early warning system was piloted in a collaboration with the local municipality. The aim was to go beyond structural defense, introducing a dual-layered system combining meteorological monitoring and physical debris detection. Here is the first layer. First layer uses a weather station to monitor rainfall intensity and temperature, especially relevant due to the role of permafrost melt. Then there is a second layer. This second layer consists of an innovative sensor system known as a tear-off sensor. And this is a mechanical device that is physically connected to a large borders in the debris path. If a boulder is displaced, something that only happens in case of a debris flow or landslide, this sensor is triggered. This provides immediate binary combination that an hazardous event is underway. The goal is combine predictive alerts with physical confirmation, allowing authorities to act confidently and immediately. So let's take a closer look at the technical setup. The system covers an area of roughly 7 by 2 kilometers, and it includes 2 weather stations that are placed at key elevations to detect intense rainfalls and temperature variation. Then there are 6 tear-off sensors. Each one is connected with multiple arms to boulders, and these boulders have a weight of at least 150 kilograms, either naturally occurring or placed for the purpose. Then at Valley there are 2 radio concentrators positioned in safe zones within the valley, creating redundancy in the communication network. There are even 2 sirens in Sonico and Rhino, plus 2 traffic lights to stop vehicles on the vulnerable bridge. Excuse me. Then there are even 2 remote cameras positioned 3 kilometers downstream for visual confirmation. So this is a wall-comprehensive early warning system. And the entire system operates on a private LoRaWAN network, ideal for isolated alpine environments where power and cell coverage are unreliable or not existing. This system is built to endure extreme temperature, humidity, and wind exposure. This is not enough robust technology. It's carefully adapted to the environmental and logistical challenges of the region. So the system logic is based on a 2-stage trigger model, pre-alert and confirmation. First, the weather station monitors rainfalls in real time. If predefined thresholds are exceeded, for example, 3 millimeters in 5 minutes for the level 1 alert, or 10 millimeters in 5 minutes for level 2 alert, a warning level is triggered. These thresholds are based on local geological analysis and historical events. Fire brigades are pre-alerted and they are prepared for a possible intervention. Then there is the second part, that is the confirmation. So if any of the tear-off sensors during the path are triggered, indicating actual movement of a boulder, the system instantly activates maximum alert. What happens next is fully automated. Sirens sounds in both the town, traffic is stopped on the bridge, and the authorities receive notification via mobile app, SMS, or email. All this takes place within 1 to 2 seconds from the event, eliminating human delay. This is very important, and this automation is critical, especially for nighttime events or during storms, when response time is limited. Designing a system for this kind of terrain isn't simple. It has typical operation conditions are altitudes above 2,400 meters, temperature as low as less than minus 30 degrees Celsius, no electricity, no mobile coverage. There is difficult access, often requiring helicopters to act. And that's why each component was developed to be self-powered, using solar energy and long-lived batteries. The TIR sensors are fully autonomous and operate on extremely low power. The system also needed to be easy to install, even at high altitudes, and durable, with zero tolerance for false positives or missed alerts. Taking account that in over 12 years of operation, the network has not generated a single false alarm, thanks to the clear trigger logic based on physical rock displacement. Maintenance as well needs to be minimal, with remote monitoring typically sufficient. This makes a cost-effective, long-term solution for remote region. Since becoming operational in 2012, the Varrabia early warning system has been activated several times during real flow events, consistently proving its effectiveness under critical conditions. The most important recent activation occurred in 2020 and again in 2023, when approximately 250,000 cubic meters of debris were mobilized from the Gallinara Valley following intense rainfall events and unstable mountain conditions. During these events, large volumes of rock, mud, and water rapidly propagated downstream, carrying boulders comparable in size to small vehicles. Thanks to the integrated monitoring infrastructure, combining meteorological analysis, physical debris detection, and automated alarm activation, local authorities received timely warnings and were able to activate emergency protection procedures immediately. In every documented activation, the villages of Reno and Sonico were alerted and evacuated before the debris flow reached the inhabited area. No casualties or injuries were reported, demonstrating the reliability of the system and the strategic importance of real-time early warning system in high-risk alpine environments. This project demonstrates how technology can become a concrete tool for protecting communities exposed to increasingly unpredictable natural hazards. By transforming environmental data into actionable intelligence, the system enables faster decisions, greater preparedness, and a more resilient approach to risk management. The Varrabia experience shows that effective early warning is not only about monitoring critical events, but about creating the conditions for safer territories, stronger emergency response capability, and greater confidence for the people living in vulnerable environments. In a scenario where climate-related risk continue to intensify worldwide, integrated monitoring and early warning infrastructures are becoming a fundamental element for sustainable protection of mountain community and critical infrastructures. So, thank you for your attention.
Thank you very much for your impressive presentation. Is there any question from the floor?
Yes, Professor.
Thank you very much for your presentation. Well, I just want to make sure that my understanding is correct. The debris flow sensor that you have, so it needs to connect directly to the borders, right?
Yeah. We connect the tier of sensors directly to the boulders, but we use even some instruments to prevent false alarm. So, first of all, the boulders must have a significant weight, more than 200 kilograms. And then we have even some bypass elements that if the boulder moves less than some small displacement, this doesn't activate. This is made in order to doesn't have false alarm, as how I have explained in several years we didn't have any false alarm. So we can even adjust the bypass in order to be more sensitive or less sensitive. And I will show you in the afternoon another application very similar, but even for geotechnical hazards. So rocky mass with cracking in the rock, and more or less the principle is the same, but adjusting the different components. So we have made this in order to have a reliable system, very simple, and avoiding false alarm. Can you?
Yeah, it's challenging to select the right rock in order to attach the system in.
We use the existing big boulders, but in some part we used even fabricated boulders. So we use a concrete weight. Yeah. I want to. Yeah. Yeah. We have made it. In the upper part, we have big boulders, but in more or less in valley part, we use fabricated boulders. So we can even switch between the two.
When the debris flow occur,
Yeah.
and then the rock slide or move, this is destroy your sensor.
Yeah, it can be destroyed. It's not a problem because they are tear-off sensors. The cord is a wire rope of 3 millimeters, so it can be broken. But the alarm is recorded, and the alarm is sent to the final user. Then there is the maintenance to be done after the event. But the sensor has made the scope for what we used it. So when there is an activation, usually there is the maintenance about this, but it's very easy. The tear-off sensor is that one, the round disc that is called the Hello Mac on the table. You will see that there are 8 ropes, and each one connected to a different sensors. And then there are long ropes. There are the bypass and all the other components. Maybe we can see better after the presentation. Thank you, Professor.
Thank you for your presentation. I have the question is that how you are considering the velocity during the debris flow?
Yeah. The velocity is not a problem for us because we, having the double layer procedure, we have the confirmation of the event with this tear-off sensor. So velocity is not a problem because they are displacement sensor. So when there is a debris flow activation, these big boulders where the ropes of the Hello Mac are connected move to valley, but velocity is not a parameter that can affect the measurement. So there is the activation, and then the tear-off sensor sense that something happened after a certain threshold, and in a few seconds all the sirens sound. The bridge is closed by the red lights, and app, SMS, and email are sent to the person in charge. So about this, we didn't have the velocity as parameter inside our procedure.
Okay, what we have observed in a project which we have implemented already, we observed that with the level, like you are doing the cross-sectional area, with the cross-section area, the level is increasing, and based on that, you are generating the alerts to the local communities to evacuate, correct? But what we have observed is that before level goes up, the water is having a push, and it depends upon the slope, and it's very critical for countries like we live in. So the velocity factor is much more critical than the level at that stages. And we have observed this back in 2010. We have a huge flood coming over there, and then with the discharge calculation of for the sensors which we have implemented over there, was not supporting the decision to evacuate the local communities. Then recently, back in 2018, again we observed the same, but with that one we were having a velocity sensors also installed. So it was a mix and match.
Okay.
Due to that, we were able to evacuate the people on the right time. So how, like, that's why this question I asked, that how you are encountering this velocity factor in this kind of scenarios. And if you yeah, I'm talking
Yeah.
later on. All right, okay.
Yeah, taking out that this is a specific network that we have created for this situation. So in this case, the velocity was not a problem, and we act with these sensors. Then the possibility of a network such this is to implement if different sensors in order to adapt to the different site condition, even if velocity is a parameter that can make a differences between decision. Taking out that we have a lot now of reference with combined networks with different sensors, and then we can add even other sensor when they are needed. So in this case, for Varrabia case history, we didn't have the necessity to use speed velocity sensor, so we did not use it. But if we have maybe a water table that is significant, we can use, for example, velocity sensors. We can use ultrasonic level if we don't have a lot of debris, but we have more risk of floods and moreover. So we can adapt everything. We can combine all these sensors in different ways to adapt to the local specificity, taking all the advantage of this system with all our sensors, because taking account that each sensor that we provide is wireless. The communication with the gateway is without any cable, so we can reach a very long range of radius, taking more or less 5 kilometers. So we can, using one or two concentrators on a valley, we can cover an entire valley with different sensors spread away.
Yeah, just adding a quick comment to Domenico's answer. I guess you were referring to flooding. And so when it comes to flooding-related early warning systems, we do measure speed. And this is part of the presentation that Domenico is going to put up on screen like in a few minutes from now. So it's kind of a similar application, but we use a different technology to measure slightly different parameters.
Yes.
Thank you very much for the clarification. Is there any further comments or the question from the floor?
Thank you for the presentation. First question is like, so does this equipment measure the acceleration?
Yeah.
Acceleration.
No, in this case, we didn't use acceleration. We use the tier of sensor that is displacement. So we connect different different sensors inside each of the device to the boulders inside the debris channel. When there is a debris flow, there is an activation of the whole bedrock, and then this movement activates the sensors. So we do not need the acceleration sensor. We bypass this. So we use this as warning system without any acceleration, but because we didn't need it.
It necessarily need to have a displacement. Does it like that? I mean, if we talk about any...
Yeah, because it's a warning system. If you have a debris flow, you have the activation of the debris.
What I'm asking is sometimes the ground can be shaken during the debris. I mean, there will be little shake. So if there is something coming up from top.
Yeah.
So the valley part could be have some kind of a slight shake that where we do some kind of accelerometers in our monitoring systems as well. So that's what I'm asking. So if this does not need any displays, I mean the acceleration, but the displacement measure in terms, that is also acceleration meter, right? So if it is.
So basically, for this particular application, we are looking at displacement only. But as you mentioned, there may be some vibrations in tectonic, case. So we have a lot of additional equipment which act as the plus kit, maybe, which may measure slight vibrations as well. And in the end, it's, as the professor also mentioned, once you have done a very detailed geotechnical investigation, you know that where the sensors have to be put, what are the thresholds, what are the variables you want to measure. So along with this kit, we can have other additional plus kits as well, which may cater to your particular concern about measuring the vibrations.
Smallest measurement that you measure here?
I didn't hear the first part.
What is the smallest measure we can measure from this one?
We can adapt this. Taking count that these are tier of sensors, so it's on-off. There is the displacement, there is not the displacement. So we can adapt to the specific site with physical connection. So we have, as I told before with the professor, we have, first of all, a sort of bypass that avoid false alarm. And then we can adapt with a sort, basically a slack on the long ropes that connect the sensor, because the device is installed in a safe zone outside the river channel. Then there are long ropes that come from the device to the boulders inside the channel. And if we want to avoid a specific an alarm less than a specific threshold, we can adapt this slack. But we can talk maybe after with the sensor there. I will explain in detail.
I think that should be the last question of this session. Thank you very much, for Domenico, for your
Thank you.
Impressive presentation. Now, from water-related hazard, however, not limited to mountain catchment, flooding remain one of the most widespread and costly natural risks worldwide. To explore the topic further, please welcome Mr. Salil, Business Unit Head of Defense and NESA activity across India, Southeast Asia, and Pacific. He leads the development of environmental monitoring and early warning initiatives throughout the region, support the deployment of advanced monitoring solutions for hydrological and critical infrastructure application. Salil, the floor is yours.
Hello guys, I'll just quickly move on to the next presentation. I guess Domenico has done an incredibly great job, so I will not repeat most of the stuff. Yes, so now moving from the hills to the rivers to the water bodies. Increasingly frequent extreme weather events require a brand new approach for managing the floods. The project over here shows how environmental intelligence can support safer and more resilient communities. We are not going to discuss a theoretical scenario, but we are going to dive into the Bisagno Basin case study, which is located in a very critical hydrological area of Liguria. And during intense rainfall events, the Bisagno can react very quickly. It can turn from a stream into a high flow watercourse. And between 2011 and 2014, several severe events caused significant floods in the area. And since 2020, important infrastructure works have been launched to reduce the risk. But along the development of infrastructure, it is very important to monitor the risks, the real-time monitoring that may happen and that may affect the construction and also the infrastructure which has come up. So in this context, the objective is to design a system which is capable of ensuring both the safety of people and at the same time protecting the critical infrastructure. This means being able to detect in real time critical meteorological and hydrological events while ensuring continuous access to reliable data. However, the environment in particularly challenging, complex terrain, limited accessibility and high exposure to extreme events. So the system must be highly reliable and must require minimal maintenance, because we have seen in difficult areas, in difficult to access areas, the key is the maintenance has to be absolutely minimal to zero. Another key requirement is coverage, because in, again, very complex areas, we cannot have multiple nodes which require maintenance over regular periods of time. Over here, we are not talking about a single point, but we are talking about a large area spanning around 11 kilometers. Well, this allows us to detect abnormal rainfall upstream, which is the eventual trigger to the hazard that is to follow. As of now, we have just been talking about monitoring, but monitoring alone is not enough. It's not sufficient. We get the data, we monitor the data that is happening, but the real objective is to move from monitoring to early warning. This means being able to anticipate the risk that we have gained the knowledge from monitoring, detect signals from upstream and understand how the system will evolve downstream. In doing so, we enable proactive decision making. So once we know what is happening, we should be able to take quick life-saving decisions as well. And ultimately, what makes the difference is not just the data, just the decisions, empowering the local communities as well through these proactive decision-making systems. So what do we have in an end-to-end architecture? As we have been mentioning, we are a completely wireless system provider. We first have the rain sensors. We have the water level monitoring devices as well, as one of our friends was inquiring about. So the applications are very different. So over here, we have two parameters that we are monitoring. One is the rainfall, which is usually installed upstream so that we are able to assess the amount of rainfall that is happening, and we are able to assess what effect it might have on the downstream. And then we have the ultrasonic water level sensors, which help us understand how the water level is rising in real time. All the information is relayed in absolute real time through LoRaWAN to our concentrator, which we call the UBIR. This acts as a central gateway and data aggregation unit. This then transmits the data to our Sunflower platform, as you can see, which can be installed on your laptops, mobile phones, any communication device. And the logic is absolutely simple. We collect the data on the field. The data is transmitted to a centralized unit, which is then transformed into actionable information for monitoring and early warning. This is what usual deployment looks like. That, on the upstream you have the sensor which is collecting the rainfall, and then you also have a sensor which is monitoring the water level, and then the data is being collaborated and sent to the gateway, to the UBIR, which, as I showed in the previous slide, is being monitored through our platform. Yeah, and the technology. This is the technology that enables the entire system to work in absolute real-time world conditions. It relies on LoRaWAN for long-range communication, which allows it to connect all the distributed sensors across several kilometers in very complex mountainous flood basin terrains as well. One of the key advantages is stability. The system is designed to maintain consistent performance over very long distances without the need of a large number of infrastructure. So we do not require dense infrastructure to be able to ascertain the parameters. At the same time, there is absolute no need for wired connections, because when we're talking about the field situations, if we have a lot of wired sensors, we know that the failures can lead to very high maintenance works as well. This significantly simplifies the deployment when we're talking about the non-wired, completely wireless connections, especially in very remote locations. Finally, the system is completely autonomous. All the devices are solar powered, which means they can operate independently for prolonged periods of time with minimal to zero maintenance, as I've mentioned. This combination of long-range communication, reliability, and autonomy is what makes the solution scalable and very effective across challenging environments. All the data is collected in the field, is visualized in absolute real time through our Sunflower platform, providing operators with a clear and immediate understanding of the current conditions. At the same time, historical data is stored, is analyzed, allowing for trends, patterns to be identified over a period of time. On top of that, the system is configured with custom thresholds. So we define the thresholds at which we want to identify that a particular urgency might happen. This means that when certain conditions are met, the thresholds that we have already built in, the system can automatically detect potential risks. Finally, a multi-level alert system ensures the notifications are triggered with appropriate level of urgency, supporting a structured, timely response. In this way, the data is not just collected and deployed. It is interpreted, it is prioritized, and it is turned into actual decisions. This slide explains how the system operates in absolute real conditions. So we first have our rainfall collection through the sensors, and then the data is correlated, the rainfall is correlated into the water level that may rise through the water level sensor. And once we have the different thresholds that we have actually built in, we can provide the alerts that we want to provide to the authorities, which in turn can take action. It can be relayed in the form of messages to the handheld devices. And at the same time, we have these warning sensors which can stop the traffic, which can alarm the local population as well. Overall, the key outcomes generated by the systems is first the early detection, because early detection is the key, and it allows the risks to be understood much better. And by identifying these critical conditions, the operators, they gain a valuable time to act before the impact actually happens. Second, the system operates on a fully autonomous way. The alert generation does not depend on manual interpretation that people have to actually go see and then maybe give out some warnings, which reduces the delays, eliminates any kind of uncertainty, ensures absolute consistency in critical situations. And finally, all of this translates into a tangible result, a high level protection for both people and the infrastructure. So the value is not only technological by all these systems that we are trying to build in, it is operational and ultimately about safety of people. Well, thank you. Any questions?
Thank you, Slasil. Very general question, if I'll ask that you are mentioning that you are correlating the data of the rainfall to a river profiling, correct? Now, if I don't have an upstream rain gauge and still I observe the flooding, because some intermediate rivers can enter into that river, and this is happening, and this is normal in the terrain in the Monteras region, it is. Now, based on that, how you are correlating? First question. Second thing is that, as I explained earlier, with the level, how can I predict the early warnings to facilitate the downstream? Because with the level, with the current, the defining by having a threshold defined, I can accommodate the local community nearby. But how can I inform and gain the time to inform the people at the downstream, certain kilometers away? Thank you.
Thank you for the great question. So, number one, let's say in a real-time scenario, we do not have a rainfall measurement sensor upstream. And let's say we're talking about a plain flood basin and we only have rivers, and certain streams might have an influence on the water level. So over there, we do not correlate data between two data points, because over there we just have one data point, frankly. So based on the threshold that is there on that particular data point itself, we set out the alarm that we want to ascertain, because you will have the data in absolute real time on the app on your devices as well. So when the data point is single, we do not correlate to any. We have the installed thresholds, the pre-installed levels in this particular case, and we take the appropriate actions accordingly. So there is no correlation between two data points in the first case. Secondly, which is a very critical real-time problem, that how do we actually give a warning, or how do we ensure that people downstream get the warning? That is where the beauty of this architecture comes into play. So as I was explaining that this particular project was spread over a 11-kilometer area. And let's say we have a river basin and downstream there is human inhabitation. And what we can do is, based on an event occurring upstream, and let's say by combining multiple sensors, like my colleague explained earlier, there is a tear off, there is incident, and then there is a water level increase as well. So the data is communicated through LoRaWAN through another integrator to another concentrator at the bottom where the actual human population is. And how do we give out warnings? So to the actual population, we can give out warnings in the form of, number one, alarms. The sirens will go off in that local population. If there is any critical road or any bridge which is passing by, which may get affected because of the river, the traffic can automatically be stopped through boom barriers, which are calibrated, which are integrated into the entire architecture. So through these physical actual interventions, we can provide safety to the people downstream by correlating the information of the occurrence which has happened upstream.
Well, thanks for this clarification for the if you don't have the rain gauge. My concern is a little bit more critical in terms of with the level based. I know that this much cubics of water is flowing under this particular terrain or bridge, correct? Now, how quickly it can affect downstream at what distance? How will I know this? Because that is what I will call it as a early flood warning system, based on the level.
Okay,
If I don't have the velocity, yeah.
So
please.
let's say the no more than in 3 minutes, the people downstream will get to know that the occurrence has happened. That is the least, that's the maximum, I'm sorry, amount of time it will take for the information to be transmitted. And in terms of kilometers, LoRaWAN and our sensors, they can cover anywhere between 5 to 8 kilometers of a wider area, provided there is no physical obstruction. If there is a mountain or a small hill, then you have to have repeaters, like a different concentrators. So you can cover an incredible amount of area. It just would depend on the exact location of the site.
Sorry, I want to add some information that I can answer to your questions. Of course, the level is one of the most important parameter, so for setting a threshold and so on, but it's not enough, and often is absolutely not useful for creating an alarm and so on. Because often you have a situation where you can face the erosion, for example, of the piers. The erosion of the piers is something that is very dangerous. It can destroy it and make the collapse of the bridge, or similar situation. Or in other situation, you need to monitor the discharge of the river. We can cover the same way this situation, and you will see in the afternoon we have a specific presentation specifically for the erosion of the piers and the monitoring of the flow of the rivers. So we can answer exactly to your question on how we solve this kind of problem with this kind of technologies. Okay.
Thank you very much, Basito. And for sure, I like to have it and put it in your mind is that I want to know, and we need to know that this amount of water flowing downstream at what rate it is flowing, and how quickly I have the time to evacuate the downstream people. Based on this decision, I want based on the velocity flowing for a particular terrain. So this is what if you can
Exactly. But this is the monitoring again, and our approach is a little bit different because we have an approach according to the early warning. I mean, there is a problem, I inform you, I switch on the siren, I stop the traffic and so on. And then I can give you the information and you can evaluate, you can make your assessment and so on. This is the approach.
Yeah. And adding up to what Pierluigi and Salil just said, as we speak, actually a couple of months ago, we were asked by the very same local municipality to make like an extension to this Bisagno River basin because they also want to know how long it's going to take for the water before reaching like critical assets. I guess that's your question, right? So basically, what we are going to be doing now, actually between September and October, we will be installing additional sensors, which are going to be part of the exact same infrastructure, is an extension, where we will be measuring also the flow velocity. And that's a key parameter, right? So how long is it going to take for the water to reach critical asset? It depends on where you are measuring the flow, right? So the further away you are, the longer notice you may have. So in this case, we were given a few parameters. So a few like hydrogeological studies were conducted. So we were asked to install the additional sensor in very specific locations, which are the locations that technically are the most critical. On the other end, that's where you want to know if something is going wrong, so you can get or you can give as further notice as possible to the local population. So that's why we are making this extension, including like also like water speed measurement sensors. So
you are planning to have this kind of sensor installing on the upstream. So yeah, it makes sense because it depends upon the slope and with the velocity, and then how the water, how quickly it can go to certain terrain. Yeah, okay. So if you are planning to have that additional sensor, it makes sense. Yeah.
It also depends on the distance between the measuring point and the critical asset.
Any further comments from the floor? So I will continue the next section. Why the flood presents the visible face of water management, and equally important challenge lie beneath the surface. Let us know how to explore environmental monitoring support and management of groundwater and subsurface water resource. Please also continue. Welcome, Mr. Sali.
Yeah, so you have me for another session, guys, so kindly do bear with me for another presentation. So yeah, moving on from the mountains to the rivers, now to actual ongoing projects, because there is so much of infrastructure development which is going on around us, and it is very critical to ensure we monitor the effect that development may have on the environment around us. And we know that water resources are often invisible but absolutely essential. So this project over here reveals how continuous monitoring can transform hidden environmental processes into very good actionable information. Large infrastructure projects can potentially generate significant impacts on surrounding ecosystems and groundwater resources, especially given excavation and earth-moving activities that usually happen with large infrastructure projects. During the construction of a major highway bypass in southern Italy, our client required a method where continuous environmental monitoring of infrastructure was capable of verifying whether construction activities would have any sort of effect on the quality of groundwater and on the nearby water body surfaces. And this is something that we usually see now, even in areas like mining, when a project of mining is being undertaken, what effect it would have on the nearby ecological setup. To ensure continuous environmental supervision throughout all construction phases, a distributed monitoring network composing of surface water stations and deep piezometric monitoring points was deployed across 3 macro areas of Cassano, Voltura, and Montella. The project aimed not only to collect environmental data, but to establish a reliable real-time control infrastructure capable of supporting environmental protection, compliance verification, and rapid identification of any possible contamination event that may happen during the construction life cycle. Well, the challenge: monitoring groundwater and surface water quality during the construction of any major infrastructure project, it presents various technical and operational challenges. The monitoring infrastructure had to operate across multiple distributed geographical areas, combining surface water monitoring with deep piezometric installations positioned along the construction corridor. The system also needs to be functional and needs to function in harsh and continuously evolving construction environments, where accessibility, installation conditions, and operation stability could rapidly change as the construction phases move. Another key challenge was guaranteeing autonomous long-term operation in remote locations through solar-powered stations while maintaining reliable acquisition of multiple environmental parameters which were set forth before the project. At the same time, the infrastructure had to ensure various continuous real-time transmission of environment data towards a centralized cloud platform, enabling the operators to continuously verify the groundwater conditions were fine and the identification of any anomaly that may happen because of any contamination because of the construction activities. The project was deployed with the objective of protecting the groundwater and any nearby surface water resources. Also, at the same time, the monitoring network was designed to enable continuous environmental supervision through distributed measurement stations. The infrastructure also aimed to support real-time environmental control, allowing operators to identify any and every anomaly that may happen. The architecture is similar to what we have been mentioning throughout the presentations, that it is a very modular architecture. The monitoring infrastructure was designed as a distributed environmental supervision network, which is capable of continuously collecting, transmitting any groundwater and surface water data in absolute real time. Field monitoring stations were deployed across the construction corridor, combining groundwater monitoring points installed on piezometric wells with surface water monitoring stations positioned near the rivers. Each station integrated autonomous power supply. Also, environmental data collected from the field stations were transmitted, in this case, unlike the previous case study, through 4G cellular communication network. And the platform, again, our Sunflower platform, provided the operators with continuous access to all the environmental conditions. This gives a complete idea of the field deployment, where we can see the various kinds of sensors being deployed across the entire construction corridor. And as I mentioned, the connectivity in this case was not LoRaWAN, it was 4G. And in various difficult areas like on the hills, we can have satellite connectivity as well. And the tech, the groundwater monitoring station is designed to supervise the aquifer conditions through continuous acquisition of water level. Over here, we're talking about underground water level and the water quality parameters as well. Each installation integrates industrial data loggers, autonomous power supply systems, and multi-parametric probes. The infrastructure combines calibrated instrumentation, communication technologies, and real-time data transmission to guarantee continuous acquisition and continuous monitoring of the parameters. The surface water monitoring station is designed to monitor rivers, as we were discussing in the previous case study as well, reservoirs, canals, and any and every kind of water body. The system uses multi-parametric probes, where we are able to assess the quality of the water as well. And the robust and weatherproof design guarantees reliable, long-term operation and reduced maintenance requirements, even in under highly variable flow and environmental conditions. Again, on the Sunflower app, you can see the deployment of the various sensors. You can have a look at the various parameters that have been pre-built and the changes on a real-time basis. And from absolute raw data, you have a very good water quality map, which is giving you enough information to make calculated, well-informed decisions. And again, the operational logic is very simple and very similar to all our systems. You first acquire the data through the sensors, which is then sent to the cloud, where you acquire all the data, where you validate all the data. And through the Sunflower app, you know where your deployment is, you know the entire map of the system, and you're able to get the information and understand the information really quickly. And as we had showcased in previous case studies as well, you can have the threshold depending upon the parameters that you have sent in and the actual information going to the users in the form of SMS, WhatsApp, any emails, any real-time alerts if needed. So the key outcome is the project, it gives a strategic step towards strengthening long-term resilience towards groundwater monitoring. The idea is to have a proactive supervision, is to be completely aware of the operations that are happening on the ground, what effects it may have on the ecology, and to have a proactive model that the right decisions can be taken. Potential critical conditions are to be identified at a very early stage so that we are able to take the corrective measures so that the development of infrastructure and the environment can be in harmony and can move forward together. This is it from my side. Thank you so much for your kind attention, everyone.
My name is Mauro. I'm from MedGeo in Thailand. Multi-parameter sensor. Now they have a new challenging type of construction that is a data center for AI. And this data center, they suck a lot of water from the ground and they change not only the groundwater level, but even the quality of the water. They have a big discussion in Texas, in Tennessee for the new data center that is reduce a lot of the level in the ground and affected the village and the town around this area. Which kind of parameter and how they can be used to identify the quality of the water for the drinkable water in this case?
I think when we're talking about the potable water for suitable drinking quality, we have the regular 7 parameters like pH and all that. We do not relate the water which is being going to the STPs because that is a different ball game altogether. But in this particular case, 2 very important parameters. One is the groundwater level because, as you said, they are drinking up a lot of the groundwater. That is the first level of monitoring. And once they have used that water and is being sent out, let's say into reservoirs or into rivers, then we have the usual water quality temperatures like the CO, all of that, the usual which are accepted by the WHO. So these are the 2 key parameters that we are able to monitor. I think everyone got everything. So that's it from me, guys. Thank you so much for your attention and your time. Thank you.
Throughout this morning, we have explored the wide range of applications from landslide, debit flow monitoring and flood management, groundwater monitoring, and environmental intelligence. Now, for the next section, we're going to have the panel discussion. I would like to invite all the lecturers on the stage. While those challenges may appear very different, they are shared common objective, transforming environment data into the actionable decision that improve safety, resilience, and sustainability. Today, we have privilege to having with us the expert and representing different sectors and perspective. I would like to start to asking each of them to share their thoughts and how environmental monitoring is involved and what roles technology will play in the future. The first question to our keynote speaker, Professor Sutisak Solam. Professor, your research has focused extensively on the rainfall trigger landslide, geotechnical hazard mapping, early warning system, and tropical environment. From your perspective, how can geotechnical engineer contribute to transforming environmental monitoring data into practical risk mitigation strategy for vulnerable communities?
Okay, as in my presentation, you can see that part of the warning system is to do the modeling. So geotechnical engineer can involve in terms of understanding the mechanic or the behavior of the material, of course, and then need to work closely with the geologist in order to quantify the risk that may happen in the future. Not only just to use the classical geotechnical model, but in the future need to go further into the probabilistic analysis to taking into account of the uncertainties that may occur. Of course, for the natural material that already have the uncertainty in its values. So in order to make the appropriate threshold for the warning system, which is based on the geotechnical modeling, we also need to take into account the uncertainty of the material, is the geomaterial, and also the uncertainty of the load, which is the precipitation. Okay. One of the audience asked about using the accelerometer or the vibration sensor to monitor. That's one of the things that may be relating that what we are talking about here. Of course, you can monitor the vibration, but you need to have an appropriate model to make sure that that vibration came from the sliding. You can see that we can have monitoring, of course, but we need to have the appropriate model and appropriate model to taking into account the uncertainty that is going to occur to properly quantify, what should be the appropriate threshold of that. Okay, so that's why when I talk about the community base, the reason is, of course, if we have a good system, just like NESA have, which is good, but we still have the uncertainty in nature. That the fact that is embedded inside. So if we have both the system that is quite systematic, plus the system that came from the people who live in the community, maybe the gap of the uncertainty will be closer, will be narrower. So double safety for the warning, something like that. So come back to the question. Maybe I go too long. Geotechnical engineer, of course, need to stick on the behavior of the rock and soil material that can be degraded, or the strength will be dropped by the increase of the precipitation or water pressure. That's all. Or water pressure, to be exact.
As follow-up, how do you see predictive landslide modeling involved in the coming years?
Well, it have to be focusing on the micro zonation area instead of just focusing on the large area. Maybe it should be coming more into the micro area or small area, in which you need to have a specific or the precise instrumentation that put into that area. But the challenging thing is how you prioritize the area that you need to install. Okay, because as I already mentioned, for example, in Thailand, we have about 10,000 villages that prone to the landslide. How can we do the risk prioritization of that? That's another challenging things. Of course, we don't have much money to install all 10,000 villages. That's too much. We need to start the most risk one, and then followings. And how can we prioritize without any bias? For example, bias from the political point of view. That's also always distort something.
We know something about it.
Yeah. All right. So that's my response.
The next question to Mr. Domenico. The climate change increasing in the frequency and also intensively extreme rainfall events in the mountain region. Based on your experience, what are the biggest challenge in designing reliable debit flow early warning system to remote and harsh environment?
Well, the main feature that it's very important is to have a system that can be very reliable under extreme harsh condition. Taking account that operating in a mountainous area, we have a lot of position where we didn't have any power, any electricity, and so we need to provide systems that must be very reliable. So self-powered system.
The microphone. You have.
Yeah. It's better to change. Okay, maybe this one is better. So we need a system that must be self-powered in order to operate under extreme harsh condition. Then even system that doesn't need any internet coverage in the position of installation, and that's why we operate with radio system, so we can have the data outside of the harsh condition zone in order to operate in all the conditions that we want. Then there is even another challenge, that is the fully reliability of the system. So, as I told during my presentation, avoid false alarm. So we use simplified models, simplified devices in order to have directly an information without the need of extremely elaboration of a lot of data. So that's why we operate in this way.
And how important is to combination predictive methodological threshold and direct physical detection system?
Yeah, it's very important, the combination between the two layers that I showed you before for the Sonico case history, because with the environmental model, the environmental parameter, we can make prediction of the events. We can make pre-alert operation, like as I showed, we can make in alarm the fire brigades in order to have a quicker response when the second layer activates. So when the sensor will detect a movement, will detect an event, everything can be ready to have quick operation in order to save lives and in order to better response when it's really necessary.
Thank you very much.
Thank you.
To Mr. Salil, flood monitoring systems are becoming increasingly strategic for urban resilience and climate adoption. What role does the real-time monitoring play in the reducing hydrological risk?
We all know that the hydrological events, they can escalate in absolute no time, and they offer a great risk to densely populated areas as well. So it is absolutely essential that we have real-time monitoring so that we can get access to the information in real time. The authorities can take informed decisions to protect the critical infra and save human lives. And when we are doing real-time monitoring, we are preparing ourselves in a much better way for future events as well. And we are able to, in fact, also design appropriate geotechnical interventions. So in terms of real-time monitorings, it's the absolute key.
And what is the key advantage of LoRaWAN and wireless monitoring architecture in geographic contribute monitoring network?
When we're talking about LoRaWAN, I think it is one of the most simplest available technology for transmission of data, especially when we are talking about installations in very remote, very difficult to reach locations. It is a much better offering as compared to wired installations because, as we mentioned earlier, it completely does away with the requirement of periodic and large maintenance. Also, through this tech, you can have an architecture which can cover a much, much larger area. And then you can have multiple, sensors, multiple parameters in that area. So for early warning and real-time monitoring, in terms of transmission of data, I think LoRaWAN is the simplest and the best, thing that is available out there.
Thank you very much for Mr. Pairuchi. We often talk about solar monitoring in terms of compliance. In your opinion, how does high quality environmental data contribute to the bankability and operational efficiency for utility scale PV plant?
Okay, it is a good questions. Of course, the quality of the data is very important for both for the reliability of the system and also for the bankability, because high quality data permit you to understand how the system is performing, how the system is working, and which is the data that you can use for establish the result of the system. This help you to reduce the maintenance, not only permit you to certify the system and then to get funds from the banks, from the insurance, and reduce the additional cost that you can have.
EPC company often seeks the comprehensive solutions that not only offer the data certified according to the current photovoltaic monitoring standard, but also can be immediately integrated into the SCADA system, typically used in PV plant. Do the solution they offer meet the requirements?
Okay, if I got well, the question is if our system can be integrated directly to the SCADA of the EPC plant and so on. Yes, of course, being a manufacturer and with a very long experience in this field of application, we developed a solution that is immediately integrated in the local SCADA. And the important thing is that normally is made directly by the technician of the EPC, not by us. We supply the goods and they can integrate it directly to the local SCADA. For the simple reason, we're using the standard protocols, the standard way for making this kind of integration. We have a great knowledge about all the protocols that are used around the world, and we try to tailor the system according to the EPC request or the customer request. This is what we are able to do.
I see. Gianluca, agrivoltaic combine architecture, renewable energy, and environmental monitoring into the single ecosystem. What are the main benefits of integrating those three dimensions?
That's a good question. Do you happen to have like an easier one eventually? So, jokes apart, I think those three dimensions can really complement each other. If we think about meteorology and agriculture, those two areas are really tied together, because if we think about like precision agriculture, so precision agriculture is something that has been around for like a decade, eventually more. And that's exactly, that's a real example of how meteorology related parameters can influence agriculture and not vice versa, of course. Nowadays, we are also adding a third dimension, which is photovoltaic. And we will talk about agrivoltaic-related application in the afternoon, which, by the way, it's like in Italy and in Europe is gaining traction very, very fast. It's also heavily subsidized by the European community, especially over the last couple of years. Not sure that's the case in this part of the world. But basically, you can see how eventually also the photovoltaic can benefit from meteorological application. And again, in the afternoon, we will touch on a case study where basically we develop a solution that is creating exactly this correlation between these three different dimensions. So the benefits are multiple, of course. So you can have like a more resilient ecosystem as a whole, by combining those three dimensions together. And also, if you think about creating a correlation between photovoltaic, so it's like renewable energy production and agriculture, then you can influence each other in a way that you can get the best out of both worlds. So you can have like eventually a better production of your crops, for example, as well as you can maximize the energy production.
I see. And in your vision for the vineyard in the future, how important is the real-time microclimatic monitoring for improving productivity and sustainability?
Yeah. So that's exactly what I was referring to. In the afternoon, we will see exactly that case study, which basically is creating a correlation specifically on a vineyard. The key advantage with this specific application is the vineyard is very sensitive to climate change. The grapes are heavily dependent on temperature and water and humidity and other different parameters. So we will see that when it comes to this specific application, we are measuring parameters such as temperature, air humidity, soil moisture, soil temperature. All of these data then are coming together in a way that there is an algorithm that is enabling us to again get the best out of the wine production as well as the energy production. So, and again, that's the new frontier of the monitoring. Here we are not talking about early warning, of course, but again, is a very tangible example of how we can use the same data we are collecting for early warning related application, for example, in a completely different vertical, in a completely different environmental, still giving our customer a competitive advantage over the market.
I see. This issue is also interesting for Thailand and also this region because we mostly likely do agriculture a lot. And if your technology can improve our productivity and also have the renewable energy, that's going to be the win-win situation in this topic.
That's why we came all the way here, right?
So yeah, thank you very much for being here. Today we have discussed very different application. There is flow, flood, groundwater, solar energy, and agrivoltaic. Despite those different, what are the common technology elements shared across those projects?
Well, the common factor is, despite all the difference, the different sector that where we can work, is about the reliability of the system, first of all, and even the communication, the architecture of the system, how we manage the data, how we collect the data from the environment itself. Then we can have agriculture, solar, hydrogeological parameter, and moreover. But what we want to ensure is the reliability of the system and an easy access to the data from the territory itself.
Just for adding an additional consideration, do not look at us like a manufacturer of sensor, because sensor is something that you can find everywhere. You have to look at us like some partner for developing solution. A solution means a mix of skills, of relationship, of instrumentation, of course, but a mix of different competencies that are necessary to aim in the goal, to arrive to the scope of the application. Just for giving you an example, when we develop a solution, we look around to all the possibilities, to all the consideration. For example, the Halo Mark that we have developed for the debris flow, for the rockfall barrier, is a device not only developed for transmitting the data everywhere or to solve the problem related to the power supply, but also in consideration of the installation that must be made by a normal technician, not by a high-skilled technician, because it's not possible to send our technician everywhere in the world. And the device has been developed to support a direct impact of 100 G of acceleration. This means that we consider also the worst condition, not only the environmental condition, the harsh condition. So everything that we are trying to do is made around the problem, not around the single sensor or the single devices.
Okay. Depends if you would like something to share.
No, yeah. If there is any other question, eventually.
I have the final question. If we met again, like another next 5 years, how do you think the environmental monitoring and early warning system will be involved? What technology or approach will have the greatest impact to the next 5 years?
Oh. Yeah, I mean, what's wrong with you? All the most difficult questions are coming to me. So, first of all, next time we meet, we said it's Mauritius, right? AI is a big piece of what's coming next, right? We are all aware of ChatGPT and the different platforms and the way they are penetrating our day-to-day life, not only business, also personal life. So right now we are exploring new venues, try to understand how we can apply AI technology to our solutions, to our products, in order to try anticipate the events. Because all we have been talking about so far and all we are going to be talking about moving on in the afternoon is early warning, is prevention. Of course, we don't have like the magic wand, for us to say, okay, tomorrow this is what's going to happen, but we can try to close the gap and come closer and closer by embracing new technologies. As we speak, early this morning, I put up on the screen like the data logger, the new IONET device. For example, that device will have AI capabilities embedded to a certain level, of course, but that's the challenge. So in everything we do day in and day out, we are asking each other, how can we make the best of today's available technology? So long story short, I don't think we have a very solid answer to your question, but we will try to answer your question as we go by relying more on one end on the statistical approach, on the other end by networking with also with the people around here, because as we said, today's goal is connecting with people that are sharing different experiences and expertise, and then pushing the boundary in terms of how can we, again, embrace new technology. AI is probably the main factor coming to play in the next steps of the products and solution evolution.
So anything could leak from your research department in your company?
Yeah, that's
Well, looking in the next 5 years, of course, AI will coming. Even in my research at the moment, I'm doing some AI with my PhD student. But I must say that the most sophisticated And the most intelligent sensor available in our world is in yourself, is a human, right? So how can you integrate the sensor that is, from the technology, from the industrial, and then um, to the people, especially the people who live in the risk area, they experience, they know, they feel every day. They experience the disaster. How come that we try to integrate the technology from industrial and the technology, which not technology, the human sensors, which is most sophisticated, of course, right? And then together with the AI system. So, for example, my imagination, my own imagination for 5 years, next 5 years, every rain gauge would have its own threshold. The data that they, collected, the information can automatically adjust it by themselves to create their own threshold in each location. That might be, and also some other sensor as well can calibrate themselves. For example, I asked you about the before sensor. That is what is the tension, what is the force that it can pull. These are the things need to be, we set the threshold, of course, at the beginning, but it should be able to calibrate themselves somehow, right? Okay, and then that's a thing. One final thing that I need to make a comment. The successful of the warning system. I mean, we are working on the life-saving business, right?
Right.
We are saving life. To saving life, we have technology. Of course, in the technology, we have the science. We need to understand the nature of the hazard. We put the technology. But of course, you need to integrate with the culture of that area. You need to integrate with the law, of course, in the particular area. For example, I did not mention in my presentation, but the sensor that we install, in the hazardous area, in the hazard area, for Thailand, all the sensor that bought by the government is a government property. So what does it mean? It means that if there's the bill flow and then it's gone, somebody need to pay back that government property. These are the things that, of course, need to sort out, because it's not realistic. It's not good. It's not realistic. But we need to sort out and change the law together, with our experience. Okay, thank you very much.
An additional consideration from my side, I think that the technology is moving faster than the capability to understand how it's possible to do with it. And I think also that it's necessary to change the mentality and the culture, as the professor said today, to convince the population to use a new technology is very complicated. But also it's complicated to explain to government, especially because they are used to say, if something is working well, we don't change. We prefer to use that. It's true, but not always. Sometimes it's necessary to have a view that is over the limit, is beyond the capability to understand, and trust to the new possibility, for example, to the AI, that will help us imagine for the analysis for the future, what is possible to do. And we need to follow this capability, this technology for the future, but we have to move together with the changing in mentality and changing in culture. This is the reason, because we need the collaboration. We are looking for expanding our relationship around the world, because only in this way we can understand which are the real goals that we have to achieve around the world.
I see. Thank you very much for your experience and sharing the all knowledge and your expertise in the morning session. As now we conclude this morning section panel, one message really clearly emerged from today's conversation. Regardless of the specific applications, environmental monitoring is no longer simply about collecting data. It's about transforming information into operational intelligence, enabling faster decision, improved resilience, and helping communities, industries, government for better dissipate risk and opportunity. On behalf of NESA, I would like to thank Professor Sutisak Solalam, Domenico Salil, Pailucci, and John Luca for sharing their experience and insight. And thank you all for participation and engagement through the morning section. We will now take a break for lunch and networking. The lunch will be prepared at the third floor upstairs here. The afternoon section will resume at 2 when we have explored new application of environmental monitoring, renewable energy, air quality monitoring, and geotechnical and geological risk management. We encourage you to take this opportunity to meet with our speakers, exchange the idea and with the fellow participants, and also continue the discussion informally. Enjoy your lunch, and we look forward to welcome you back at 2. Thank you.
Okay, welcome to everyone again. Not easy to start in the afternoon because it depends on how much you eat, on how much sleep you got. So let's start with another case history made in Mauritius between 2016, 2018, 19 years regarding the solar energy. The energy transition begins with the understanding the resource. This project demonstrates how high-quality solar measurement can support national planning, investment decision, and the development of renewable energy. The context. Apart its national energy transition strategy, the Republic of Mauritius launched a program aimed to reducing the dependency on fossil fuel and accelerating the adoption of renewable energy resources. In this framework, solar photovoltaic energy emerged as a strategic pillar for the future national energy mix, making the availability of reliable and geographically representative solar resource data essential. At the time, existing solar measurements were fragmented, limited in coverage, and often inconsistent, creating significant uncertainty for both policymakers and private investors. To support the development of a structured photovoltaic market, Mauritius required a reliable, long-term, and high-accuracy radiometric monitoring infrastructure, capable of generating the country's first national solar map. Sorry. The availability of the reliable solar resource data represented one of the main challenges for the development of the photovoltaic sector in Mauritius. We are speaking of a project started in 2017. At that time, as I said, existing measurements were limited, fragmented, and not enough representative of the entire territory, making it difficult to accurate access to the country's real solar potential. This lack of reliable information generated uncertainty for both public institutions and private investors, slowing down energy planning activities and development of new photovoltaic projects. The project therefore requires the creation of a geographically distributed monitoring infrastructure capable of providing high accuracy radiometric measurement over the long terms. At the same time, the system had to operate continuously and reliably in harsh tropical conditions and coastal environment, characterized by high humidity, salt exposure, and difficult environment conditions, as I said. Another key objective was ensuring continuous real-time data availability, enabling the creation of a certified solar database to support national energy strategies, strategic studies, investor confidence in the photovoltaic market. So, the main objectives. The project was designed not only to collect solar radiation measurement, but to create a strategic infrastructure capable of supporting the country's long-term energy transition. One of the primary targets was the creation of a national solar database based on a reliable, continuous, and geographical representative measurement. This database would become the technical foundation for understanding the real solar potential of the territory and supporting future photovoltaic developments. At the same time, the initiative aimed to support national energy planning, all the activities by providing institutions and utilities with accurate data for feasibility studies and resource assessment and long-term strategy for solar application. Another key objective was enabling the development of a structured local photovoltaic market. By reducing uncertainty around solar resource availability and improving confidence in the quality of the data, the project helped to create more favorable conditions for investors and for the future expansion of the photovoltaic energy in all the territory. The system architecture that we provide. The monitoring infrastructure was designed to create a reliable and geographically distributed network capable of continuously measuring solar irradiance and environmental parameters across the territory. Each field station integrates radiometers and meteorological sensors specifically selected for photovoltaic monitoring application, including solar radiation, air temperature, humidity, and other environmental variables, requiring for accurate solar resource assessment, all made according to the latest standard and norms to certificate the PV plants, for example, Class A pyranometers. Unlike traditional monitoring architectures based on intermediate gateway, each station operates autonomously and transmits data directly to a cloud service called Sunflower, a web platform designed by NESA, and the transmission is made via cellular or satellite communication network, according to the place where has been installed. This simplified architecture improves scalability, reduces infrastructure complexity, and enables rapid deployment even in remote locations. All collected data are centralized in the real time with the Sunflower platform, where they can be visualized, validated, and analyzed through data dashboard or historical trends or advanced reporting tools. This approach transforms distributed file measurement into a centralized and continuous update solar resource database, support long-term investor and long-term monitoring. File deployment. The file deployment phase focused on installation of a geographically distributed monitoring network designed to accurately represent the solar resource variability across Mauritius and the Rodrigues Islands. Multiple automatic monitoring stations were installed in different environmental and climatic conditions, including coast areas, urban zones, and inland regions, ensuring broad territory coverage and reliable long-term measurement. Each station was specifically configured for photovoltaic monitor application and equipped with radiometric and meteorological sensors. And each station is capable of continuous measurement solar irradiation and environment parameters for the application. Particular attention was dedicated to long-term operated reliability with autonomous power supply system and robust infrastructure designed to operate in tropical and coast environments. The result network creates a certified and geographically representative solar monitoring infrastructure, forming the technical foundation for the deployment of the National Solar Resource Database and the future photovoltaic planning activities of the Mauritius Island. The technology. The monitoring station deployed for the project were specifically designed to ensure high accuracy solar resource measurement and reliable long-term operating in tropical conditions. Each station integrates Class A secondary standard pyranometers for accurate solar irradiance measurement. You can see one of the sensors over the table, the back of the room. Together with the air temperature and the humidity sensor for complete environmental condition and monitoring, and also include a reference shell or soil shell, depending on the application, to certify the photovoltaic performance and to validate the quality of the data. All stations are also equipped with industrial data logger backup batteries and solar power system, ensuring full autonomous operation even in remote location. To guarantee continuous data availability, the station integrates both cellular and satellite communication modems, so the transmission is made in both ways, enabling real-time remote transmission for all measurement to centralized cloud platform for monitoring, validation, and analyzing the data. The monitoring infrastructure developed by NESA was designed to ensure the continuous acquisition, transmission, and centralization of high-quality solar resource data collected across the territory. All measurements acquired by the distributed monitor station, including solar irradiance and environment parameters and photovoltaic reference data, are transmitted in real time to the centralized cloud platform, where operators can locally and remotely monitor the station status, validate the measurement, and access to the historical data by desktop or by mobile devices. The platform provides a unified environment for data visualization, storage, and export, enabling institutions and technical stakeholders to access reliable and geographical representative information from all monitor sites. Within the project framework, NESA were responsible for the deployment and the operation of the monitoring infrastructure, as well as for the collection and transmission of the radiometric data. The acquired dataset were then made available to the Mauritius Department of Energy, which used the information to perform the solar resource assessment activities and develop the national solar map, supporting the country's long-term photovoltaic planning strategy. Beyond the deployment of the monitoring infrastructure itself, the project also included training activities and technical knowledge transfer initiative aimed to strengthening local expertise in solar resource assessment and photovoltaic. Technical personnel from local institutions were involved in dedicated training programs covering station operation, sensor management, maintenance procedure, data acquisition, and other methodologies. Particular attention was given to solar measurement technique, because the interpretation of radiometric and environment data used for photovoltaic application is very important. The initiative also contributed to improving the understanding of photovoltaic system and solar resource monitoring practices, enabling local teams to progressively develop operational autonomy in the management of the infrastructure. By combining technology deployment with the capacity building activities, the project created the foundation for the long-term sustainability of the National Solar Monitoring Network and supported the development of local capability and skills for maintaining and expanding the infrastructure in the future. The key outcomes. The project generated significant strategic benefit for the development of the photovoltaic sector in Mauritius, extending well beyond the deployment of the monitoring infrastructure itself. One of the most important outcomes was development of the local technical expertise through the dedicated training activities and knowledge transfer programs, as I said. The initiative also played a key role in enabling the deployment of a more structured and mature photovoltaic market. By creating a reliable national solar resource database and supporting long-term energy planning activities, the project established the technical foundation required for the future expansion of a utility-scale photovoltaic project and renewable energy investment across the country. Another major outcome was the reduction of investment risk associated with photovoltaic project development. The availability of reliable long-term and geographically representative solar resource data enable institutions, utilities, private investors, and insurance to perform more accurate feasibility studies and energy yield assessment, increasing confidence in future renewable energy investment. I remember we are speaking about a project starting 2016. That's all, and thank you for attention.
Thank you very much. Any question from the floor? Let me see if it from the online. What the technology innovation do you believe it is the greatest impact for the solar energy in your topic?
Yeah, in terms of innovation, it's a good question because, as you know, we are manufacturer of all the radiometric sensor. I mean, pyranometers, class A, class B, class C, and so on. That logger and a complete system that is capable to interface directly to the SCADA system of the solar plants. But we have introduced an additional innovation in the few past years that is based on the same technology we showed this morning with the file link, with the sensor can be installed everywhere on the plant and connected via radio to the main station. This means that you don't need wire connection. You don't need a specific additional station to monitor specific parameter. You need only a sensor with a wireless connection. We developed the same technologies used for the other sensor that we saw this morning and we will see after again, that permit us to cover wide areas. We are speaking about 5 kilometers radius of area with big plants that can be installed, and where you can install single radiometer, single sensor, depending on the application that you want to monitor, the measure that you want to monitor, and collect the data directly from the single data logger or the single point. This permits to reduce the cost, to reduce the maintenance, to improve the accuracy of the quality of the data.
Good chance for Thailand too, as we are one of the hottest country in the world in the tropical zone. Our sun got very high capacity here, I believe. So that's your product would be very good chance for us to apply in the field too. Is there any question from the floor? If not, thank you very much for your presentation. Now we have seen how accurate in environmental data support the performance, reliability, and bankability of large-scale solar plant. But what happens when energy production must coexist with agriculture productivity? It is where agrivoltaic create new opportunity. Please welcome back Gianluca.
So here we are back to the 3 dimensions we talked about this morning during the Q&A session. So let's again open it up with a quick question. So can agrivoltaics do more than generate clean energy? So that's a big question. This project explores how environmental monitoring and data-driven management can transform an agrivoltaic installation into a smarter, eventually more productive and resilient vineyard. So, Caviro Group is Italy's largest wine cooperative, manages a highly diversified agricultural ecosystem distributed across multiple territories and climatic conditions. The increasing frequency of extreme weather events, combined with growing ESG requirements and the need for resource optimizations, highlighted the necessity for a more integrated and data-driven agricultural management approach. To address these challenges, Caviro initiated the development of an advanced agrivoltaic vineyard where photovoltaic production, environmental monitoring, and precision agriculture, so exactly the 3 dimensions we talked about this morning, could operate as a single interconnected ecosystem. The objective here was not only to generate renewable energy, so that was one of the objectives, of course, but also to improve vineyard resilience, optimize irrigation and microclimate management as well, and support more sustainable agricultural practices through continuous environmental data acquisition and intelligent control system. So, one of the main challenges of the project was increasing resilience, as we just said. So against climate variability and extreme weather events, which eventually are becoming increasingly critical, as we have seen this morning, for modern viticulture, heat stress, strong winds, and rapidly changing environmental conditions can significantly impact both vineyards' productivity and photovoltaic infrastructure capability. Another key challenge involved centralizing environmental and agronomical intelligence into a unified ecosystem capable of continuously collecting, transmitting, and analyzing real-time data coming from multiple distributed sources. Ensuring reliable access to accurate environmental information was also essential to support faster and more effective operational decisions. At the same time, the project needed to overcome the traditional conflict between vineyard productivity and photovoltaic shading. Conventional agrivoltaic systems often create static shading that eventually can negatively affect vine growth, grapes quality, and overall agricultural performance if not dynamically managed according to the real environmental conditions. So here, the ultimate goal was to create a dynamic agrivoltaic ecosystem capable of continuously adapting photovoltaic exposure and agricultural management according to real-time environmental conditions. So one of the main challenges of the project was managing vineyard microclimate variability across the whole agrivoltaic infrastructure while maintaining optimal growing condition for the grapes. At the same time, the system needed to balance crop productivity and renewable energy generation by dynamically and continuously regulating photovoltaic exposure according to environmental conditions and agronomical needs. So another key objective involved preventing damage caused by extreme weather events such as heat stress, hail, that's another factor, and strong winds, minimizing risk for both events such as heat stress, such as, again, agricultural production and photovoltaic assets. So the infrastructure also needed to optimize water consumption, of course. And that happened through continuous environmental analysis and more efficient irrigation management strategies. Finally, last but not least, ensuring continuous environmental monitoring and centralized access to agronomic and energy data was essential to support real-time operational decision across the entire agrivoltaic ecosystem. So this is the system architecture. Looks a little bit tricky, but it's not that tricky. Actually, to support Caviro's agrivoltaic vision, NESA and our technological partner, we need to develop an integrated monitoring and agronomic intelligent ecosystem designed to connect all the environmental data, vineyard management, and photovoltaic control within a single and adaptive infrastructure. So NESA agrometeorological stations installed across the vineyard continuously acquire environmental and agronomic parameters, including air temperature, air humidity, solar radiation, wind, rainfall, of course, soil moisture, soil temperature, and leaf wetness through a WMO and UNI-EN compliant set of sensors. Data collected in the field then are transmitted through the FieldLink LoRaWAN infrastructure to the Evolution data logger, and then securely transferred via 4G connectivity to a certified data server, cloud-based actually, ensuring reliable real-time data availability, validation, and storage. Environmental information is then processed by our technological partner agronomic platform, which integrates microclimate analysis, irrigation optimization models, alert management, and adaptive agronomic intelligence to support operational decision-making. The platform also enables dynamic photovoltaic management strategies capable of regulating panel inclinations, so then controlling solar trackers, according to real-time environmental conditions. So that is meant to improve vineyard resilience, crop protection, of course, at the same time, water efficiency, and renewable energy performance within the agrivoltaic ecosystem. So all of these factors were combined together into a single infrastructure. So this is a quick layout of what the installation looks like, in real life. So as you can see, the agrivoltaic deployment is based on a distributed environmental monitoring network designed to provide continuous real-time visibility across the whole area. So multiple peripheral agrometeorological stations that we refer to as nodes installed throughout the vineyard are actually measuring key environmental and agronomical parameters, so that I was referring to before, so air temperature, air humidity, solar radiations, and then again, measuring soil-related parameters and rain, of course. And so all of the stations are communicating wireless through the FieldLink LoRaWAN infrastructure. So the central station that you can see, up there, the big one, the big guy, is actually acting as the communication hub for the entire monitoring network, collecting and validating data coming from the nodes, and then eventually securely transmitting them to the cloud platform through 4G connectivity in this case. This architecture enables reliable long-range communication, as we have seen multiple times also this morning. I mean, the infrastructure is exactly the same, applied to different verticals. simplified field deployments and continuous environmental monitoring, supporting adaptive vineyard management and real-time operational decision-making. So in this case, the agrometeorological stations were specifically designed to support advanced agrivoltaic and precision agriculture application. So the one that you see here up on the screen is an evolution of our standard precision agriculture related meteo station. Its all-in-one architecture integrates the main environmental sensor that I was referring before within a compact and robust field device capable of operating reliably in demanding outdoor environments. So every single node is equipped with high precision WMO compliant sensor. And so every station continuously acquire key parameters and then securely transmit them to the cloud-based platform. So the station is fully solar powered, so there is no need for any kind of trenching. You don't need to run any wire. You don't need to create any infrastructure to power the weather stations, the nodes, allowing autonomous, very low consumption operation without the need for external power infrastructure, as we said, therefore minimizing installation complexity within the vineyards. I'm not sure you are familiar with vineyards, but vineyards is a very, very fragile ecosystem. So you cannot go there and start, digging holes and running trenches. So because that really would mess up the whole ecosystem of the vineyard or the vineyard itself. So that's why this solution was designed specifically for permanent outdoor deployment. So it's rugged construction, low maintenance required, and long-term operational reliability, which makes this solution ideal for continuous agronomic and environmental, in this case, agrivoltaic environments. So as we said, environmental data then are collected by NESA and continuously transmitted and processed real time. So through the integration between our monitoring infrastructure and the agronomic decision support platform, operators can monitor microclimatic conditions, irrigation requirements, environmental risks eventually, and photovoltaic operating conditions 24/7 across the whole installations. So real-time analytics and automated alerting support are actually also supporting faster and more informed operational decision, which at the end of the day is all meant to support and to optimize vineyard resilience, water efficiency, because then this way we can also reduce, irrigation, water consumption, and create the proper balance between agricultural productivity and photovoltaic performance. So, as we said, all of these factors combined contributed to improving the overall efficiency and sustainability of the ecosystem. So through continuous analysis of the environmental and soil conditions, then the system enabled, for example, a more efficient irrigation, which eventually leads to reducing unnecessary water consumption while maintaining optimal growing condition throughout the vineyard. In this specific case, we were able to prove that with this ecosystem, the water consumption was reduced by as much as 30% compared to the previous year. And we all know, water consumption is one of the big challenges for future generations, for the generations to come. So at the same time, real-time monitoring and adaptive agronomic management contributed to increasing vineyard resilience as well. Improving vineyards resilience mostly against climate variability, heat stress, and rapidly changing environmental conditions, again, supporting a more stable and sustainable crop development over time. Again, here we are talking about food. Food scarcity is, again, a challenge for the generations to come. So eventually, even though our contribution is going to be 0.00001%, that's our way to try contributing to, kind of making the world a better place eventually for future generations. So all in all, the integration between all of these parameters and supported by intelligence, eventually, intelligent ecosystem and adaptive photovoltaic management also enable a more optimized balance between renewable energy production and agricultural productivity, so improving the overall efficiency and long-term sustainability. So in other words, the way this system operates is that there is an algorithm embedded into it that is capable of reading all the environmental parameters and then determining whether the system has to give priority to the energy production or to the crops. So if the energy production, like the daily target is met, then eventually you can give priority to the crops. Or if the crops are suffering because sun exposure or eventually heat stress, then eventually we can operate the solar tracker to create shadow over the crop and vice versa. So the crop already received all the water, all the sun, the irradiation that they needed. Then again, we can go back and produce eventually more energy. So that's all balanced out by reading all the data coming from our monitoring infrastructure. Thank you for your attention.
Any question from the floor?
Thank you, Jurka. It's quite interesting and really the aim which you are putting in front of us to have the world a better place to live and for the future generation, for sure. Yeah, we have the responsibility.
Very high.
Yeah,
Very high, right?
Yeah. Jurka, one question is that since we have all these parameters taken out from the sensors like soil and the leaf wetness, particularly controlling the water usage of the crops, there is one parameter which we need to have in the precision agriculture, that is the crop health itself. Like when it requires some kind of sprays, pesticides or something. So can we have this in this data analytics tool which you are looking to?
Yeah.
Thank you.
That's a very good question. Thank you for asking. So I was referring to our technological partner that we worked with to develop this specific application. And as we speak, we have a few more projects coming up with the exact same type of technology. So our technological partner happens to be, actually is an Italian base, used to be a startup, now is a scale up, is part of the BASF organization, BASF, like the chemical company, the Germany, guys. And basically, they developed a software which is called DSS, which is like a decision support system, which is basically developed specifically for every single type of crop, whether it is maize, it's, fruit, it is whatever it is. So in this case, of course, they use the vineyard, the grape algorithms. And basically, they were able to correlate all the different parameters, humidity, temperature, sun exposure, in a way that eventually that algorithm is also capable of returning an information based on, hey, there is this risk of this kind of, bacteria, or you need to irrigate, or there is like a fertile irrigation need, or there is too much water. So all of these informations are become available via this platform. Right now, if I'm not wrong, this software covers, I think, 28 different type of crops and fruit. And then as we move forward, not NESA, but our technological partner is introducing more and more solutions to cover more and more crops. I understand that based on now, vast majority of the most popular one are in there. And the way they put it together is also based on statistics, because this is exactly what they've been doing also like in the past 10 years. So, and now that technology allows, they are trying to push the envelope in a way that eventually we can turn data into eventually predictions, say, hey, be careful because if it doesn't rain in the next 10 days, then you have to go there and spray some chemicals to protect the crops or whatever it is. So it's available today. It's not a NESA piece of information is not a NESA platform, is our technological partner platform, but yeah, it's available.
The NESA platform and that platform will be acting with each other, yeah, to provide the field.
Yeah. Basically, and this is like a real life example of when we said early this morning that eventually we can also integrate our solution with third parties, software platforms, solutions as well. So in this case, the end user, the Caviro guys, are not connected to our own data platform. They are connected to our technological partner data platform. So via API, we are making data readily available for them real time to be, integrated into their database, to be like used, processed, and then to create a report for the end user.
Look also very attractive too. That's the compliment to your dashboard. And any further question from the floor?
Yeah, I just want to ask, what if any extreme event happened, like how the system responds? Like, let's say we have a very long drought period, or like a cyclone that affects for the rainfall. When prediction levels goes wrong, like something like that.
Yeah, probably. I'm not sure I am the most qualified person to answer this question because, again, the platform is not like a NESA platform. But basically, of course, as I said, all the feedback coming from this software is based both on statistical analysis and eventually also on weather forecasting. Of course, if there is like an extreme event, like a tornado, well, we don't have tornado, fortunately, in Italy, but we do have extreme events, hails, for example. And if that happens, then probably then it is an assessment from like a professional, like an agronomist is needed, because I don't think extreme events were mapped into that platform. But eventually, as I said, I'm not the most qualified person, but I'm gonna take a note on your question, and then I will pass it over to our technological partner and come back to you in the next few days so I can provide you like a proper answer to that question.
If we didn't have any further questions from this section, John Lucas still with us for the next question for air quality monitoring. In the next section will be about our case study to completely different environment, showing how the same monitoring principle can apply to the protection of cultural heritage. So please still welcome Gianluca.
So, okay, let's change subject here. By now you probably learned that I love to open up my session with a question, right? And so the question is, what if monuments could tell us how the environment is affecting them? Because this is exactly what we're going to be talking about in the next 15, 20 minutes here. So this project here is a perfect combination between environmental monitoring and scientific research to better understand the relationship between air quality and cultural heritage. So in order for me to do that, I'm going to take you all back to my beautiful country. In the very south, in the deeply south of the country, there is a city called Matera, which is a UNESCO heritage. If you guys haven't been there, I would highly recommend you to go there and visit because it's quite unique. And the whole town is carved out of stone. It's really unique. set. So the stones of Matera tell a story that spans literally thousands of years. But today, those same stones are telling us something more, how they respond to the environment that surround them and how the environment is changing because of the climate conditions. So every change in temperature, every period of elevated humidity, and every episode of atmospheric pollution leaves a mark on this unique cultural heritage. These processes are often slow. Most of the time, they are invisible to the naked eye, of course, because it takes dozens, sometimes hundreds of years. Yet, over time, they can significantly influence the preservation of historic buildings, monuments, and urban spaces. And that's all over the world, of course. It's not just in Italy. To better understand these interactions, an integrated environmental monitoring network was deployed across the whole city. So the goal was not to simply collect environmental data here again, but to transform information into knowledge, in this case, eventually providing continuous insight into air quality and local microclimate conditions. By listening to the environment, which is the thing that we always try to do at the best of our knowledge, we can better understand how the city evolves. We can eventually support scientific research and provide conservation professionals with the tools that they need to protect one of the world's most extraordinary UNESCO World Heritage Sites for future generations. Again, the future generation is something that keeps on coming around over and over. As Professor Satisak said this morning, at the end of the day, all we try to do is to protect lives. That's all really matters at the end of the day. So by ensuring reliable environmental monitoring within a centuries-old urban landscape, it really required the deployment of a robust and, in this case, non-intrusive infrastructure that was capable of operating continuously while respecting the architectural and cultural value of this site. So the project faced the challenge of, for example, establishing distributed monitoring locations across historical centers, ensuring representative coverage of different urban environments while, of course, minimizing visual impact on the UNESCO heritage setting. Continuous air quality assessment was also required to measure concentration of atmospheric pollutant that may contribute to stone weathering and surface degradation. At the same time, the network needed to support detailed microclimate characterization of the urban canyons, where narrow streets, varying elevation, and complex architectural geometries create highly localized environmental conditions. Beyond real-time observation, the system also had to enable long-term environmental trend analysis, providing researchers and conservation authorities with the information they needed to identify patterns, correlation, and potential risks over time. Finally, all collected information needed to be transformed into actionable intelligence, as we always try to do, through real-time access to environmental information, allowing stakeholders to visualize conditions, analyze historical data, and support evidence-based heritage preservation strategies. So, at the end of the day, the project was designed to create a permanent environmental observatory capable of supporting the preservation of Matera historic landscape through objective, measurable, and continuously available information. Rather than focusing on isolated measurements, the initiative aimed to establish a structured framework for environmental knowledge generation, enabling researchers, public authorities, and conservation professionals to access reliable data sets and better understand the relationship between environmental condition and cultural heritage. At the same time, the project sought to strengthen the role of environmental monitoring as a decision supporting tool, providing a scalable foundation for future conservation policies, scientific studies, and sustainable heritage management initiatives. So the goal here was to create an infrastructure that eventually could be replicated throughout other very ancient cities in Italy, because we have plenty, but eventually even outside of Italy. So the monitoring infrastructure was designed to provide a comprehensive understanding of the environmental conditions influencing Matera historic stone heritage. So the system combines, again, two complementary monitoring layers. Atmospheric monitoring stations continuously assess air quality and urban microclimate conditions, while solar and rainfall stations, as you can see up on the screen, eventually measure key climatic drivers affecting surface exposure and weathering processes. Together, these distributed monitoring points create a real-time environmental observatory across the historic center. So it's important for you guys to visualize that the historic center of Matera is very small in extension, but it's very different. So if you measure the microclimate conditions in the four corners of the city, you will be surprised by how different parameters such as humidity and air temperatures are. Matera is also not far away from the wind, from the sea. So the wind blowing is creating a specific micro condition one end of the city, which is totally different, to the other end. So that was also the challenge for us. And we worked in collaboration with the Department of Civil Engineering of the University in Naples to identify the proper spots that we needed to monitor. So again, here, as it always the case, all the measurements are securely transmitted through, in this case again, cellular network, 4G, to the Sunflower platform, where environmental data are again integrated, visualized, and analyzed. Again, this is yet another case where the University of Naples were granted access to the data set, again, live, 24/7. They just get into our cloud-based platform, pull the data for them to create their analytic models that eventually can determine the next step to preserve the city. So as we said, this is the layout. Again, the extension is relatively small. It's probably like one block of Bangkok area. But yeah, it was, as I said, strategically deployed across the historic center, creating a real-time observatory capable of capturing the environmental variability of one of the most unique urban landscape. So, as I said, as I was anticipating, monitoring locations were selected to represent the diversity of conditions found throughout the city, including historic squares, densely built urban areas, panoramic viewpoints, and sector characterized by different level of solar exposure. One thing that we found being particularly interesting here is that we realized right after installing the weather station is that also public square being populated by visitors throughout the year, the visitors themselves were changing the microclimate conditions. And that's yet another challenge, because you want to have as many people as possible visiting your beautiful country. At the same time, you want to be aware that the more people are coming, the more challenging it becomes to somehow preserve, the city itself. So this approach basically allows the network, this layout, to capture both localized environmental dynamics and broader spatial patterns influencing the preservation of the city. So again, one more time, by combining atmospheric monitoring station, solar related data, rainfall monitoring points, so the infrastructure is capable of providing continuous environmental information across the whole center, supporting scientific research, environmental analysis, and long-term conservation initiatives. Well, let's take a quick look at the technology, because here you can see quite a lot of different sensors combined into a single weather station, into a single monitoring points. So the atmospheric monitoring stations was designed to provide a comprehensive characterization of the environmental condition, as we said, around the whole city, right? So by integrating air quality monitoring, meteorological measurements, and real-time communication into a single autonomous platform, again, because of materia and because of the whole area, we couldn't run any cable again. So every single monitoring station is self-powered because we couldn't get any like wire, nothing. So the local authority were pretty straightforward, say, you just go there, you are allowed like half a day, install your weather station, turn it on, out. That was pretty much the mandate we were given. So again, the station combines particulate matter sensor, gas analyzer that you can see at the bottom, the number 6, for example. And basically, we can also monitor air temperature, relative humidity, wind conditions, solar radiation, all the data that we talked about so far. They are all combined into this weather station. And we have 13 of these weather stations spread throughout the city. So at the core of the system, we have the junction box that you see opened over there. So you can see what's in there. Basically housing a data logger, communication modem, and power management electronic, which eventually is processing and transmitting all the environmental data to the cloud platform. Again, all data are transmitted real time as usual, so I'm gonna skip you guys from repeating the same story over and over, but again, what really matters here is that this is a real life example of a weather station that combines a lot of different sensors into one setup. So in this case, I was anticipating the university from Naples, they are accessing our platform and pulling data. Still, the local municipality in Matera are using our own platform for pulling data and eventually like triggering any kind of alert to the local population. Here, of course, here we are not talking about early warning. Thanks God there is no early warning. As we said here, this area is not prone to landslide or flooding events, fortunately. But they are pulling data in a way that eventually they asked us to set threshold, for example, on air pollution. If air pollution exceeds a certain threshold, the countermeasure that the local municipality is deploying is, for example, during the weekend, no car are allowed, to run across the area. Or eventually, in recent times, they are also trying to put a limit to the visitors that are visiting the city in a single day. So they are deploying countermeasure intended to somehow count how many people are visiting the area and then eventually say, okay, that's too much, you guys come back tomorrow, which is kind of extreme, but probably is one of the most effective way we have to protect that UNESCO heritage area. And this is all made possible by referring to the data that are coming from this monitoring infrastructure here. Again, system architecture very similar. Actually, it's kind of the same that you have seen multiple times today. So basically, we have, again, environmental monitoring station collecting data, validating data, and then sending them to the cloud platform, being processed by the NESA platform, Sunflower. By now, you guys are all familiar with this Sunflower name. You're going to be obsessed in the next few days, most likely. And then environmental analysis are occurring both on our data platform and on our technological partner, the University of Civil Engineering of Naples. They are doing the exact same thing at a more like a scientific research level. And then eventually, we are also capable of triggering the alarms. One of the alarms that we can trigger throughout the local throughout the city is basically sending like WhatsApp messages to the local authorities, say this threshold of like, I don't know, pollution or air humidity or air temperature or gas concentration just exceeded the maximum limit, so do something about it. So this is what we do. Again, key outcomes. So every stone tells a story which, in this case, is literally shaped by centuries of exposure to the surrounding environment. So through continuous monitoring, hidden connection between climate, atmosphere, and material become visible, revealing how natural forces eventually gradually influence the appearance, the integrity, and the evolution of cultural heritage over time. Environmental data becomes more than a collection of measurements themselves. It becomes knowledge. By turning complex observation into clear and actionable insights, the system helps conservation professionals better understand risks, anticipate changes, and make informed decision. Again, informed decision keeps on coming back, multiple times, that protect heritage while respecting its historical authenticity. Preserving heritage means looking beyond the present. By building a long-term record of environmental conditions and their effects, the monitoring infrastructure creates the foundation for more resilient conservation strategies, ensuring the monuments, historic sites, and cultural landscape can continue to inspire future generations. And with the future generation again, thank you so much for your attention.
Thank you very much for your impressive presentation. In Thailand, we also have the problem of the air quality level in Bangkok also, and also in the northern part of Thailand. We are one of the world records sometimes, which we don't like to have to happen. So I know how important that we can have the reliable detection and monitoring for condition for the current situation, so that the government can decide what they're going to do next. So is there any question for the floor or the online?
I hope you guys are not blocking the forum together this side, right?
Say it again, please.
I'm sure you guys are not blocking the foreigners to visit these sites, right? Like as what you said, that okay.
Actually, just a few of them here and there. No, I mean, this limiting access to the historical site is something that is an extreme countermeasure, of course. But if you think about it, and you guys have never been there, I believe, but if you go there, then you realize how small, the area is. And again, the city, it's literally carved out of stone. If you go there in Christmas time, the whole city becomes like a kind of open ceiling, like Christmas area. And there are like thousands and thousands of people every single day, which is a great thing, for economy. It's a great thing for like Italy, welcoming foreign and visitors. But on the other hand, it does create a serious challenge to, protecting it, because if we keep doing the same thing we have been doing over the last, decades, probably, the next generation is okay. 10 generations down the line, they may have a problem because, preservation challenge. So again, I think in recent times, the most common, way to prevent, degradation was for the local municipality saying, okay, pollutants are exceeding, the threshold, or carbon dioxide, whatever it is, or eventually even temperature. So, okay, let's make sure we don't have like car running through the site in like every other day. So they are allowed to circulate Monday, Wednesday, and Thursday, and they're not allowed the rest of the time. So that these are the kind of countermeasures that local municipalities are deploying. Eventually, thanks to this infrastructure and thanks to the collaboration with the local university, I don't know, like tomorrow or in a month or in 10 years from now, they will come up with even smarter and more effective way to preserve the city while granting access to visitors. But nowadays, that's what they do. But anyway, you're more than welcome to come, visit us.
It will be a very less percentage of the human effect for this one. There is a lot of other parameters we need to consider, but okay. Yeah.
That the audience here also want to visit your heritage sightseeing too. Thank you very much for your presentation.
Thank you.
Now we will move from environmental analysis to geotechnical risk management, exploring technology specialty design to monitor terrain stability and infrastructure safety. Please welcome back Domenico.
Okay, here we are again. Good afternoon to all. So now we'll discuss about less than 1 hour about our solution for environmental monitoring, specifically about the geotechnical risk and even hydraulical and hydrological risk. So our solution here are branded Macaferri because NESA is a society of the Macaferri group, but they are available for directly even from NESA itself because NESA is the producer. So we know that here just a little introduction. First of all, would like to start introducing the problem. We know that natural hazards are increasing, and in the last 20 years, we know that they are doubled compared to the past due to the climate change that has a considerable impact on this. According to the United Nations Office for Disaster Risk Reduction, early warnings given 24 hours in advance can reduce the resulting damage by 30%. By the way, the definition of early warning system is a complete system that identifies potential threats and provides timely information to reduce the impact of these threats. It involves monitoring, analyzing, and specifically communicating risk to ensure proactive measures that can be taken to protect assets and ensure safety. From an investment perspective, the value of early warning system is also clear. Investing 800 million in early warning systems can prevent losses ranging from 3 million to 16 billion per year. These data show how important proactive measures are in reducing risk and also prove the economic value of the early warning system as a strategical investment. So this is why we invest a lot about this new technology. We talk about smart engineering, and this is the concept between the idea to develop all the HelloMac environment, technological environment. So this idea drove us to create a solution that allows to know where is located a protection system, to know the status of it, and receive alerts in case of impact events or other relevant events. Hello Mac, maybe you have already seen it on the table at the end of this room. It's a disc-shaped device of 30 centimeters of diameter, very light to handle. From its body spreads 8 tie ropes, each one connected to a different sensor. And with this, you can control up to 8 different points with a single device. So thanks to its limited weight, it can be carried very easily to difficult access job site. We'll note that the greater part of rockfall protection systems are installed in remote areas with any kind of power supply. And this is not a problem for our system because it is self-powered with long-lasting batteries, and we can arrive up to 10 years of durability. The maintenance is null because you install the system on the protection and you be aware only in case of impact. The alert can be received in different ways of communication because even redundancy of the system is very important. And we can use the LoRaWAN protocol. We can receive alert even by satellite where we doesn't have any internet coverage at all. Or maybe when we know that we have internet coverage, we can use GSM and 4G connection. In any case, we will have always coverage and very important, we will have redundancy of the data. 3 minutes here, it's the maximum time that occurs to receive the alert in any condition. Taking count that, as I told you, we have a redundant system. So if we have a local warning system such as sirens or red lights, it takes just a few seconds to have the road safe. So in this case, the road will be closed in almost immediately time, and then in a parallel way, the person in charge to control the system will receive the notification, the email or the SMS in less than 3 minutes. So, as I told you, even about the way to receive the alarm, we have redundancy because we have an app. We see here a screenshot of the app with all the sensors spread away on a valley, in this case. And we can receive notify via app, SMS, and email. So now I will talk about how we use LMAC to create safer communities. This is a general overview that shows different applications where LMAC can be used with great benefit for the efficiency of the solutions and the community itself that are protected by them. And for every application, I will show you some different case histories where we have provided it. Starting from the first, we use LMAC to create a smart rockfall barrier system. So, in fact, rockfall and debris flow barriers equipped with LMAC are always under control because the tie rods of LMAC are connected in different points of the interception screen. Here we can see the different points. And we can adapt even to the different rockfall barrier that can be provided. We know that rockfall barrier can have different energy level based on the resistance that we want to use on the specific site. And we can adapt the tie rods of LMAC in order to fit the specific barrier. And we have even a study with the Polytechnic of Milan in which we have defined the length of these tie ropes related to the service energy level and the deformation of the screen of the barrier to know when we exceed the service level. So in that case, we will have a warning system that will not send any false alarm, or maybe will not send even alarms when we have a small deformation. The most important thing is that we use LMAC as a warning system, so it's not only a monitoring system, because we will get the information about the alert immediately, as we have seen. So we are not forced to wait a frame time to know what happened. So we have the event, and immediately we receive the notification. This is just a very short case history. Here we are in Palmi, in south of Italy. And Palmi is well known for the beautiful seaside and panoramic trekking. But the rocky slopes that reigns over the town are very dangerous due to the quick evolution that they have making it very dangerous in the past for the community. So in this situation, something was meant to be done. In fact, in less than 3 years ago, we installed an LMAC system to the rockfall barrier, and this was a specific request of the client because he wanted to be warned in case of impact. Excuse me. So in this case, we installed 1,000 and more than 600 square meter of rockfall barrier with 3,000 kilojoules of resistance, and we used only 8 LMAC to have all the rockfall barrier evolved with this solution. An important point is that the alert are received directly by the local police, and in this case, when there is an impact, the local police can act very quickly in order to save lives and in order even to make maintenance over the barrier. So the second application are the smart drapery systems, and this is a huge picture that shows how close is the danger to the below road. And even in this case, LMAC is very helpful to act immediately in case of event. Macaferri is well known because during the years have developed a wide range of drapery systems, each one with its own specific feature, starting from double twist net to highly resistant solutions such as steel grid and even mech armor. We see here a very big slope with an high resistant net provided by us. Now with LMAC Geo intelligent monitoring, our entire range of solution gains real-time threat detection capability. We see just a quick representation of how our system in this case acts. So we can see that it acts like a spider web, and it covers a great surface in order to monitor the relevant movements under the drapery system and between the anchors. We can reach up to 2,000 square meters with a single device, creating a spider web. So here it's another typical picture, and in this case we have used LMAC in a community located in the central Italy, close to Rome. Here we are in Roccasecca dei Volsci. We see here the map. And in this case, we installed a lot of different solutions. So here we have a high resistant net that is called steel grid. We have even wire rope panels, like this one, even rockfall barriers. In this case, our customer wanted to be warned about some events that can happen on this rocky mass covered by HEA panel. So in this case, we have replied to its need only with one LMAC. One LMAC was enough to have the warning system on the HEA panel. And even in this case, with LMAC, the community feels safer. Another application is the retrofitting. Retrofitting is a term that is growing more and more during the last years because safety standard changes, technology evolves, and already existing solutions of every producer, not only Macaferri, against rockfall, have the need to be evolved too. So LMAC is a solution that fits perfect for this scope because with few simple operations, it can be installed in already existing solutions, not affecting the initial geometry of the system. So here we can see a network provided to protect an important railway in northern Italy. several square meters of draperies have been equipped with LMAC. We can see the LMAC installed inside the red circles. And in this case, with LMAC, our customer knows immediately when there is a movement and save people inside the trains. Here is another picture. And in this picture, we can see how our system can work in difficult condition here with my mouse. Because we can see that here there is no external power, there is no sunlight at all. Thanks to our technology, this is not a limitation, and LMAC Geo is always working. And specifically for this customer in Northern Italy, only to a single track, we have 95 devices for about 800 detection points spread in 8 kilometers of track. Last but not least, LMAC can be used even to recover information on rocky mass or debris channel without any solution installed at all. Okay. So, in many cases, there is the need to know the evolution of a rocky slope or a debris flow without installing a structural solution. And even in this case, LMAC Geo is the top device to access and manage the risk associated to these situations. In this case, LMAC is a predictive instrument that can provide the history of the movements. Thanks to this history of the movements, we can be very effective to know where to install and which structural solution evaluate and then design. We can see that LMAC is not only an instrument, but a technological environment with many other useful kits. And this is another case history, because in this case, in Aosta Valley, we used LMAC to make a sort of early warning system to monitor and to track the evolution of this big rocky mass. Here we have a rocky mass with a very huge volume. We are talking about 240 cubic meters of rock that is already detachment, as you can see. In this case, we already have an event 2 years ago, and this is the track of the event. After that event, we provided 2 rockfall barrier at valley, upslope to a regional road, and then we have designed after the first event a sort of monitoring system in order to warn people that are interested on this road. So in this case, we used two different extensometers to monitor the evolution of the openings in the road. Then we used even one LMAC at the top of this rocky mass in order to be warned if there is a big collapse. And then we used even LMAC at valley in order to have a confirmation that the rock has impacted the barrier. So if in this case we have created a formula inside the network that the road is closed when the LMAC when the LMAC sends that there is a detachment. Then, if there is no confirmation about the event at valley, the impact on the barriers, the roads automatically can be opened, because this means that the phenomenon has not arrived to valley. Then, if in other case there is the impact on the barrier, the roads keeps closed, because that means that all the dynamic has impacted the barrier. So we have worked together with the technician of the Aosta Valley region in order to use this logic formula. So these are some pictures of the installation. We can see here the extensometers. We call it rock displacement control kit because we provide a single kit. In the next slide, I will show you more detail. They are self-powered system. We can see here that a kit is composed by a sensor plus an interface that provides power to the instrument and sends data in the same protocol to the gateway that can be located even at 5 kilometers of distance. And then here we can see the LMAC. And even here we can see the bypass that we used in order to doesn't have false alarm in case of passage of animals and moreover. So with this case history, we have seen that we can combine HelloMac Geo is an environment, and we can combine this with a lot of different kits. So these are the name of the most common kits that we can provide. This is my favorite slide because this slide shows the architecture of the system. So how the data are transmitted. So we see that in a big area with 5 to 8 kilometers of radius, we can have a lot of LMAC and Kit Plus spread over. All of this sends the via radio protocol, so we have seen in LoRaWAN or moreover, sends the signal to a single ABIR, and then the ABIR, if we have some local alert systems connected to it, directly close the road or maybe warn the people with a siren or moreover. Then, in a parallel way, with satellite or mobile coverage, the information is sent to the data center, to the data server, excuse me. The data server is used to store data and alerts history, and then these data are accessed by the user with an HTTPS protocol. So we know in this case that the great advantage that you will have with HelloMac Geo Plus is the fact that you will always have only one data collection for different parameters, controlling everything by the app on your phone or maybe an access via browser. So just a quick overview about the different Kit Plus. This is the rock displacement control kit. This is used to measure millimetric displacement to track wall and rock movements. We see here another application. And here is the interface. This interface is a common component to all the different kits, but we can see even here in this room. This is just a screenshot, a graph of a rock displacement control kit installed. We can see the evolution of an opening. The data are collected automatically with an high frequency. In this case, one data each 30 minutes. So there is no need to a person to go on site to check with a USB card or moreover. Everything is transmitted directly via satellite or via GPRS or 4G. Then another kit plus is the slope displacement control kit. We use this kit to precisely monitor landslide slopes and large slow-moving masses. We see here a case history provided. And it's very interesting because we have, in this case, 3 slope displacement control kit to track shallow landslide. And we see here with the violet dot the position of the gateway. So we see that we have 4 kilometers of distance. The gateway is close to the town in order to be in a safe position, far from the dangerous area. Inside the same network, we can provide the climate control kit. The climate control kit measures rainfall, temperature, and air humidity. And we use it to have an environmental monitoring of the area. excuse me, we see here two installations. Here, taking count that these workers are the standard workers that install Rockfall barriers or nets. Because everything is pre-assembled, they have only to screw some nuts, and moreover, the system is already pre-activated, so they need to screw just a small nut, and the system transmits there directly. And this is a screenshot taken from our platform. We can see humidity, temperature, and rainfall during a certain time period. Then we can add another kit to the climate control kit, that is the wind control kit, in order to add even direction and intensity of the wind. All the kits are meets the more intense standard that are on the world market. So everything is well approved. Another kit is the groundwater level control kit. With this one, we can track the groundwater level variation due to deep landslide. And in this case, we measure waterhead variation in centimeters or millimeters. In addition, we can use even stability control kit to monitor deep masses movement and slip surface. In this case, it's, we measure bioaxial angular displacement of masses. And here, this is a nice picture because in this case, we can see the superficial part of an inclinometric column made up by 5 stability control kits, with each one with its radio interface. In these cases, we arrived at 20 meters of depth. And this is just a representation of the data on our app. As I told you, our system can even automatically activate CNA panels, sirens, and gates in case of an event. And here are some picture of an installation. We can see here on the top part a rockfall barrier that was equipped with Hello Mac. And here we can see the gateway that is called Eva Beer. The first control box for the light, in this case, luckily the light is not red, and even a second control box for the light in the opposite side of the road. So if there is an event, a rock that hit the barrier and activate the LMAC, all the light turns red and the road is closed and directly safe. So we have seen we use only one data logger to monitor different, to use different kits, different sensors for different way to for different parameters. So even the app is only one, and everything is fully wireless. There are some questions about this part.
Sure, Dr. would like.
Can the Hello Max do work inside a mining tunnel?
Yes, Hello Mac now can be used even inside the mining. We have already some project. It's a feature that we have implemented during the last year, and in this case, for mining site, we can connect the data to Wi-Fi present inside the mine. So if we are talking of a big mine that usually have Wi-Fi, we can make a transit for the data to this Wi-Fi and then collect and see the data on the web platform. Taking count that the web platform It's not a closed platform, but if you have a proprietary platform, you can access the data with the API protocol. So we can work even in this way. So everything is even safe because the service level agreement of the data server is 99.99%. So everything is very safe. But about your question, yes, we can even use this system in mine. We already have some projects.
The audience?
Maybe one more questions.
Yeah.
So
Please.
on the big areas of the slopes, how do you select the locations to place the HelloMac?
Well, it's important to have a geomorphological report from geologists. So in this case, we provide the instrument. We can give some suggestion, but geological report, it's very important because in this case, give me, I want to show you here. Like in this case, here is a simple picture, but I have other picture about this specific site where there is the geologist that may say, okay, we can use LMAC here to monitor this specific rock. We can use another arm of the LMAC to monitor this other rock. So in that case, it's important a report from the geologist. We can give some suggestion, but it's always important this. Then about rockfall barrier is simpler because rockfall barriers is a more standardized way to install it. We know that rockfall barrier is made by multiple spans, so we know that we have to use 4 points for each span. So in that case, it's simple because the rockfall barrier is a standardized solution. But like in this case, geotechnical geomonitoring application, it's very important to know what the geologists say, even in this one.
How about the limitation of one instrument to detect this slope stability?
Yeah, usually we provide HelloMac even with some long rope skids. So 8 ropes, each rope long 12 meters. Taking count that depending by the specific site, we can provide longer ropes up to 50 meters. But even this depends by the specific site. If we have a very regular site, it's easier to reach longer distance. But if we have a very steep site with a lot of changes of inclination and moreover, we suggest to reduce the area of each single device in order to have best sensibility.
There any questions from the floor? So that we will move to the next section,
Okay.
to deep dive. HelloMac Hydro closely connect to those challenge hydrological process, which often play the critical role in triggering and accelerating natural hazard. Please continue. Welcome, Domenico.
Thank you again. So HelloMac Hydro is strictly connected to the first part of my intervention this afternoon because the architecture of the system is almost the same. What changes are the devices that we use to monitor. So in this case, we can see here the HelloMac Hydro device. Even this one, for us, is a device created to make smart engineering. Because HelloMac Hydro, this device is a smaller sensor than the HelloMac Geo. We can see there even a sample. But even if it is smaller, we didn't have make it less reliable, because even in this case we have a device that can work up to 5 years with a single long-lasting batteries with no external power needed. So in this case, we didn't need a solar panel, we didn't need direct power. Even in this case, we have 5 kilometers of range of seamless data transmission, always connected. And in the next slides, I will show you how we use this sensor. Elon Hydro, even in this case, is an environment of different sensors, different kits, each one with the same philosophy at the basis. So zero cables to make the connection. So we have fully wireless, no strings attached. Zero setup, because every sensor every kit that we provide is plug and play, no setup hassles, no installation risk. And this is very important because due to the fact that everything is plug and play, it takes only 5 minutes to install one sensor, because it directly sends its data to the gateway. So there is no limitation of coverage, because we have seen we can use satellite, GPRS, 4G, IoT, and LoRaWAN. In this case, we can see a system that is the multiparametric probe that was already showed even by Pierluigi. We have 7 parameters to monitor the water quality from every angle. We can store 3 years of data with 8 gig of data stored, always available. And in this case, this multiparametric probe is powered by solar energy with an extra battery for 7 days of power without any sun needed. So, as done before, I will show you how we create safer communities using this device and this environment. This is a map of standard application. Starting from the first, we use the environment of Elon Hydro to create smart bank protection. In this case, we use this kit here to make to make monitoring about gabions and matrices. We know that our gabions and matrices as Macaferri provide durable protection to prevent bank erosion. And with Elon Hydro, we make them smart, integrating a simple non-invasive sensor that triggers an alert when water levels exceed a predefined safety threshold. This safety threshold can be set tailored for each site. Then the second application is the smart bridge monitoring, and this is very important because in this case our smart bridge monitoring it's a system that is made by 2 different components. So we know that monitoring rivers need infrastructure such as bridges in order to pass. And we have faced a lot of issues, even in the recent past, connected even to the erosion at the basis of the pile. And we use Elon Hydro specifically to have a combination of monitoring system and alert system. Monitoring system because we provide this ultrasonic water level in order to track water changes, in order to make some predictive system and to make a pre-alert operation. Then we use the Elon Hydro Scour, these other components, in order to know the erosion at the basis of the pile. So we see here that we have 2 arms. These 2 arms are connected then to a big boulder inside at the basis of the pile, And if we have erosion at the bases, this mass will move, will go down, and then we will have the alert in order to act immediately. The philosophy is the same of the standard LMAC Geo, and is very effective. Then smart quality monitoring, we use the multiparametric probe, as we have seen. And this is, we are using a lot this, even to monitor the water level, the water quality, even after some works upstream. So we know that when there is a job site, when there is a work, maybe the water quality, the water parameters can change and can be affected by the work itself. And using this, our client can control and can track even the variation of different parameters. So we have pH, redox, conductivity, and moreover. And then we have even the smart quay monitoring. We use always the small Helmac Hydro scour, this one here. We can see that is connected even here to a mass that is put at the basis of the bank. And even in this case, when there are the big ship that will attract and can with the power to move, they can make a lot of erosion. Even in this case, we can track the erosion at the basis of the bank and get a warning. So this was the last slide. There are some questions about the hydro.
Is there any question from the floor?
Just now I saw there is an application together with a Gabion. How does it look like in detail? What kind of measurements?
Excuse me, could you repeat?
The Hello Max together with a Gabion.
Yeah.
Just a little bit to confirm. You will talk before I...
How does it look like to be installed, and what kind of measurements is going to get out?
Okay, so I go one moment to the slide. Like this one. So in this case, we installed before like in this case, we can have an existing Gabion or the matrices work, or maybe a new one. If we have a new work where we have to install even the Gabions and the matrices, we can use the Helmac Hydro. We can install it before the Gabion work. But if we already have Gabion and matrices, we can perform a vertical hole and put it inside. And in this case, we can adjust the water level due to the different direction of the specific sensor. So we can adapt it depending by if it is a new construction or maybe a sort of retrofitting of existing Gabions and matrices. And then taking count that we can combine even this one with the smart bridge monitoring, so even ultrasonic level monitoring system, and even the Helmac Hydro Scour, this one. No, excuse me, this one. This. So it depends. We can adapt it depending of which are the site conditions. So even in this case, we can make a tailored solution in order to fit specifically what we have in the specific site. Other questions?
Is there further questions? I think we also have the demonstration over there. Maybe after the open demo area, we can make the further discussion later. Thank you very much.
Thank you.
We have now reached the conclusion of the formal conference program. I would like to invite Mr. Pairuji to, for wrapping up today the events. Please welcome Mr. Pairuji. You use podium or you use over there? I think we better use the first one.
It was. Okay, just to close this long session today, I hope it has been interesting for you. You got a lot of information, a lot of different point of view, and a different approach for several applications in which we are involved in from the past years up to now, including the mitigation, not only the instrumentation, but also the mitigation through McAfee solution. I hope also that you enjoy, stay with us according to the long trip that we have done. And a special thanks to all the guests, all our partners, and in particular to the Professor Satisak from the university that I hope you came here just for a present that I want to give you. For you, and thank you to all of you for being here with us. Okay, thank you very much. Thank you very much. Thank you also to all the guests that are connected from remote. I want to use this moment to say hello to everyone, to everybody, and then let's see. Hope the next year or in the next opportunity to meet together. Thank you again.
At this point, we will conclude the live streaming session for our remote participant. Thank you for joining us online. On behalf of NESA, thank you for joining us and for your active participation throughout the day. We hope that our presentation and discussion have provided valuable insight and new idea for your project and the market. For attending person, we now invite you to join us the open demo area at the back of the conference hall, where you can have the opportunity to see the technology present today, interact with our expert, and discuss specific application relevant to your organization. Thank you once again, everyone. And now we conclude the today program. I would like to thank you all to the speaker, partner, customers, participants, and their contribution and active engagement through the day. Today's discussion has demonstrated how environmental monitoring is becoming an increasingly important tool to improve the safety, sustainability, and operation efficiency across many industries. We hope that our events will provide valuable insight and new opportunity for collaboration. We also like to express our sincere appreciation to our regional partner and contributors, Matteo Lassi, Kanika, Mito Expert, Test Tech, and MBMed for your commitment and collaboration in making of this event a success. And most importantly, a heartfelt thanks to every one of you who are in this room, our guests, customer, engineer, researchers, and partner across ISEAP region. Your presence, your questions, and your engagement have made today truly meaningful. Should you have any further technical question, our speakers and NESA team member are delighted to speak to you individually. It has been privilege to serve as your MC today. We hope you leave here inspired, informed, energized, and we look forward to see you again tomorrow for our partner alignment section. Thank you very much and have wonderful evening. สวัสดีค่ะ